Hello there and welcome to Science for Sleep, where curiosity gets cozy, the universe slows down just enough for us to look around, and science takes the scenic route toward rest. Tonight, we are turning our attention to one of the brightest and strangest objects in all of astronomy, something so powerful that it can outshine entire galaxies, yet so far away that its light may have been travelling toward us since long before humans ever looked up and wondered what the stars were. Tonight, we're asking a simple question with a not-so-simple answer. What is a blazar, really? Now, a blazar is not the name of a space dragon, although, honestly, it does sound like one. It is not a new brand of telescope, not a sci-fi weapon, and not something you accidentally create when you leave a microwave running in a physics laboratory. A blazar is a real cosmic object, and it belongs to a family of galaxies with very active centres. But that plain little description does not quite prepare you for what is going on. Because at the heart of a blazar is a supermassive black hole, the kind of black hole that can weigh millions or even billions of times more than our Sun. Around it, gas and dust are being pulled inward, heated, squeezed, stirred, and pushed to extremes that make ordinary stars seem almost calm by comparison. And from that violent centre, a narrow jet of energy and particles is launched across space at nearly the speed of light. The special thing about a blazar is that one of those jets is aimed almost straight toward us. That is the part that makes the whole object feel oddly personal. Somewhere far across the universe, in the centre of a galaxy we'll never visit, a black hole is feeding, spinning, and launching a beam into space. And by chance, by geometry, by the simple fact that the universe has directions, that beam points our way. Not because it knows we're here. Not because Earth is important to it. The blazar is not waving at us. It is not trying to get our attention, though it is doing an excellent job of it. It is more like standing far away from a lighthouse, except the lighthouse is powered by a supermassive black hole, the lamp is a jet of high-energy particles, and the ocean is the deep universe. So before we go any farther, let me ask you something gentle. Where are you listening from tonight? Are you in a quiet room, with a phone glowing softly beside you? Are you near a window where the sky's dark enough to see a few stars? Or are you somewhere bright, where the city lights hide most of the universe, but not the thought of it? And if you could point in one direction and know that somewhere out there a blazar was shining across billions of light years, would that make the night feel larger or strangely calmer? If you find this kind of journey soothing, if it helps your thoughts settle while still giving them something interesting to hold on to, I would be ever so grateful if you gave the video a like and maybe subscribed. It helps this quiet little corner of space reach more people who might need a slow, thoughtful pause before sleep. And of course, if this turns out to be so interesting that it keeps you awake, then I do apologise. But at least you will be awake with a supermassive black hole for company, which is not the worst kind of company, as long as it stays very far away. Settle in now, let the day loosen its grip a little. We're not in a hurry. Blazars have been shining for millions, sometimes billions of years, so they can spare us a few slow minutes. We can begin with the simplest picture and build from there step by step, without forcing the universe to explain itself all at once. A blazar is, at its core, a galaxy with an unusually bright and active centre. Most large galaxies, including our own Milky Way, contain a supermassive black hole in the middle. That may sound dramatic, but in many galaxies the central black hole is fairly quiet. It sits there, massive and dark, not eating very much, not drawing attention to itself. The Milky Way's central black hole is like that most of the time. It has moments of activity, certainly, but it is not currently blazing with the kind of power we see in a blazar. In a blazar, the central black hole is surrounded by material that is falling inward. This material does not simply drop straight in, as if falling down a drain. It forms a hot spinning disk called an accretion disk. Gas in that disk rubs against itself, heats up, and glows. Near the black hole, conditions become extreme. Gravity is intense. Magnetic fields become twisted and stretched. Particles are accelerated to enormous speeds. And under the right conditions, some of that material does not fall into the black hole at all. Instead, it is launched outward in two narrow jets, one from each side of the black hole's surroundings. This might seem strange at first. A black hole is famous for trapping things, not throwing them out. But the jets do not come from inside the black hole. Nothing escapes from within the event horizon, the boundary beyond which return is impossible. The jets are launched from the region around the black hole, where matter, magnetic fields, and rotation interact in ways that are still being studied. The black hole helps create the conditions, but the beam itself is born outside the point of no return. That distinction matters. It is the difference between saying a locked room is throwing something out and saying the storm around the locked room is hurling debris down the street. When one of those jets points close to our line of sight, the active galaxy is called a blazar. This alignment changes everything. The jet's light is boosted by the effects of relativity, because the particles in it are moving so close to the speed of light. To us, the blazar looks much brighter than it would from another angle. It also appears to change quickly. Its brightness can rise and fall over days, hours, or sometimes even shorter timescales. Imagine watching a lighthouse beam pointed directly into your eyes from across an ocean, except the beam flickers because the engine behind it is a supermassive black hole swallowing matter in a distant galaxy. That is not a perfect comparison, but it gets us close enough to begin. What makes blazars especially useful to astronomers is that they shine in many kinds of light. Human eyes can see only a narrow slice of the electromagnetic spectrum, the part we call visible light, but the universe speaks in many other forms as well. Radio waves, infrared, ultraviolet, X-rays, and gamma rays are all part of the same broad family of light, just with different energies and wavelengths. A blazar can shine across that whole range. It can be seen by radio telescopes on Earth and by space telescopes that detect X-rays and gamma rays. In fact, blazars are among the most common objects detected in the gamma-ray sky beyond our galaxy. That tells us something important. A blazar is not merely bright in the way a lamp is bright. It is energetic. It is violent in a physical sense, even if from here it appears as a tiny point of light. The particles in its jet are moving at speeds that make ordinary motion seem frozen. Electrons spiral through magnetic fields and produce radiation. Photons gain energy through interactions with fast-moving particles. The result is a cosmic source that can send high-energy light across distances so large that the numbers become hard to hold in the mind. Some blazars are so far away that the light we detect began its journey when the universe was much younger than it is now. Looking at them is not just looking across space, it is looking back into earlier cosmic time, and yet, for all that power, a blazar can still appear in a telescope as a point. That is one of the humbling things about astronomy. The most extreme objects in the universe do not always look extreme at first glance. A star, a quasar, a blazar, a distant galaxy, all can appear as small lights against darkness. The difference is hidden in the details, in the spectrum, in the variability, in the kind of light arriving, and in the patient work of astronomers who ask, again and again, what exactly are we seeing here? The word blazar itself has a slightly unusual history. It comes from combining ideas around BL-Lacerti objects and quasars, both connected to active galactic nuclei. BL-Lacerti was first thought to be a variable star in our own galaxy because it changed brightness. Later, astronomers realized it was not a star at all. It was the active center of a distant galaxy, seen under special conditions. That is a wonderfully human mistake in a way. Something looked like a nearby flickering star, but it turned out to be the heart of a galaxy far beyond our own, with a jet aimed toward Earth. Astronomy is full of moments like that. We name something based on what it seems to be, then later discover it is far stranger, and the old name stays like a little fossil of our first misunderstanding. Blazars are part of a larger group called active galactic nuclei, often shortened to AGN. This simply means that the centre of the galaxy is producing far more energy than the combined light of its ordinary stars would suggest. In an active galaxy, the central black hole is feeding. Matter is falling inward. Energy is being released. Depending on the angle from which we observe the galaxy, and depending on the properties of the jet and surrounding material, we give these objects different names. Quasars, radio galaxies, Seyfert galaxies, BL-lac objects and blazars are all connected in this broader family. The differences are not always about completely different engines. Often they are about how that engine is arranged and how we happen to view it. That is a quiet but important idea. In astronomy, perspective matters. The same kind of object can look very different from different angles. A galaxy with jets seen from the side may look like a radio galaxy, with long structures stretching outward into space. A similar object seen with one jet aimed almost directly toward us may become a blazar. It is like looking at a flashlight from the side compared with looking straight into the beam. The flashlight has not changed, but your experience of it has changed completely. In the case of a blazar, relativity makes that difference even stronger. The jet's light is concentrated and boosted in our direction, so the object appears brighter, more variable, and more extreme. This also means that blazars are rare in the sense that only a small fraction of active galaxies will be lined up just right for us to see them this way. The universe contains many active galaxies with jets, but only some are pointed close enough toward Earth to be classified as blazars. That makes each one a useful accident of alignment. We are not seeing the universe from a special central location, but we are sometimes lucky enough to have a cosmic beam aimed near us. The result is not danger. These objects are far too distant to harm us in any ordinary sense. Their radiation spreads across enormous distances, and by the time it reaches our telescopes, it is information, not threat. A blazar is not a weapon pointed at Earth. It is a message from an extreme environment carried by light. There is something calming in that, despite the violence of the source. The universe can be loud in energy but quiet in arrival. A photon may leave a jet near a supermassive black hole, cross intergalactic space for billions of years, pass through regions where galaxies gather and regions where almost nothing exists, enter the outskirts of the Milky Way, move through our solar system, reach Earth, and finally be recorded by an instrument built by curious primates on a rocky planet. That is not a rushed process. It is one of the slowest deliveries imaginable, and yet it arrives with precise information about where it came from. When astronomers study blazars, they are not just admiring brightness. They are trying to understand some of the most efficient particle accelerators in nature. On Earth, particle accelerators require huge machines, carefully controlled beams, powerful magnets, and teams of scientists. In a blazar, the universe runs its own accelerator on a scale that makes our machines look very small. Charged particles are pushed to extreme energies. Magnetic fields guide and twist them. Radiation pours out across the spectrum. By studying this light, astronomers can learn about physics under conditions we cannot reproduce here. The blazar becomes a laboratory, not in a neat room with white walls and labelled drawers, but in a distant galaxy, around a black hole, with the results delivered through space. There is also a practical challenge. Blazars change, they flare, they dim, they surprise us. A quiet blazar can suddenly brighten, and a bright one can fade. This means astronomers often study them using many telescopes at once. Radio observatories may watch the long-wavelength emission. Optical telescopes may track visible changes. X-ray and gamma-ray observatories look for high-energy activity. Sometimes neutrino detectors and gravitational wave observatories become part of broader searches connected to energetic cosmic events. The modern study of a blazar is often not one telescope looking alone, but a network of instruments listening to the same object in different ways. Think of it like trying to understand a distant storm by using every sense available. One instrument hears the thunder, another sees the lightning, another measures the pressure change, another tracks the wind. Each gives part of the story. With blazars, one telescope detects radio waves from extended jet structures, another catches gamma rays from the most energetic processes. A third watches how the brightness changes with time. The full picture is built slowly with patience, comparison, and a willingness to accept that the object will not make itself simple just because we would like it to. So, what is a blazar, really? At this first pass, it is an active galaxy whose central black hole launches a jet aimed close to Earth. It is a bright, variable, high-energy source powered by matter falling toward a supermassive black hole. It is a cosmic lighthouse, but not one built for us. It is a distant laboratory for extreme physics. It is a reminder that black holes are not only dark endings, but can also be connected to some of the brightest objects we can observe. And it is one of the clearest examples of how much astronomy depends on direction. The same engine viewed from another angle might seem less dramatic. Point it toward us, and suddenly the universe looks straight back. For tonight, we can hold that picture gently without needing to solve every detail at once. Somewhere far away, a galaxy has a restless center. Matter falls inward. Magnetic fields twist. A black hole spins in darkness. A jet forms and races outward at nearly light speed. Across a distance too large for ordinary imagination, that jet sends its light toward us. We receive it not as heat on our skin, not as sound in our ears, but as faint signals in carefully built instruments. Those signals tell us that even in the deepest universe, far beyond the stars we know, there are engines still running, beams still shining, and galaxies whose centers are anything but quiet. To understand why blazars are often described as some of the brightest beacons in the deep universe, it helps to begin with a simple comparison. Imagine standing in a dark field at night, holding a small flashlight. If the beam points away from you, you might barely notice it. If it sweeps sideways, you may see a faint glow in the air. But if the beam points directly into your eyes, suddenly that modest little flashlight becomes almost impossible to ignore. A blazar works with a similar idea, except the flashlight is powered by a supermassive black hole. The beam is made of particles and radiation moving at nearly the speed of light, and the dark field is not a field at all, but billions of light-years of space. That is the first key to their brightness. Blazars are not just powerful because they produce huge amounts of energy. They are powerful to us because their energy is aimed in our direction. The universe contains many active galaxies with jets, but most of those jets point somewhere else. We see them from the side or at an angle, and they can still be impressive, with enormous radio structures stretching far beyond their galaxies. But when one of those jets is lined up almost directly with Earth, the whole object changes in our view. It becomes brighter, faster changing, and more extreme. It becomes a blazar. Now, this does not mean the blazar is close. In fact, many blazars are very far away. Some are so distant that the light reaching our telescopes began travelling when the universe was much younger. Yet they can still stand out across those distances because the jet is doing two things at once. It is producing tremendous energy, and it is sending much of that energy in a narrow direction. A normal galaxy shines in all directions through the combined light of its stars. A blazar, by comparison, can behave more like a focused beam. It is not spreading its most intense signal evenly across the sky. It is concentrating it along the path of the jet, and we happen to be close to that path. There is also a second key, and this one comes from relativity. When material moves close to the speed of light, the light it emits does not behave in the simple way we might expect from slower objects. The radiation can be boosted in the direction of motion. Astronomers call this relativistic beaming, and it is one of the reasons blazars look so bright. The jet is racing toward us at enormous speed, so its light is compressed, intensified, and directed forward. The effect is a bit like the sound of a siren changing pitch as an ambulance approaches, though with blazars we are dealing with light instead of sound, and with speeds so great that everyday examples begin to wobble under the pressure. Still, the basic idea is friendly enough. Motion changes what we observe. If the jet were moving slowly, we would see its radiation in a less dramatic way. But because the particles in the jet are moving at nearly light speed, and because the jet is aimed close to us, the signal is boosted. This makes the blazar appear much brighter than the same object would appear if we saw it from another direction. In other words, the blazar is not only bright because of what it is bright because of where we are. That small fact is easy to pass over, but it is one of the loveliest tricks in astronomy. Earth is not at the centre of the universe. It is not in a special cosmic throne. It is one planet around one ordinary star in one ordinary spiral galaxy. And yet, sometimes, by chance, a beam from an object billions of light years away points near our tiny location. We become part of its geometry. Not important to the blazar, perhaps, but important to the observation. The universe does not need to notice us in order for us to notice it. When astronomers call blazars beacons, they are not exaggerating much. These objects can outshine the combined starlight of their host galaxies, at least in certain wavelengths. That means the centre of one galaxy, powered by a black hole and its surroundings, can appear brighter than the billions of stars around it. Think about that quietly for a moment. A galaxy is already an enormous thing, a city of stars spread across tens or hundreds of thousands of light years, and yet the central engine of a blazar can dominate the view so strongly that the host galaxy becomes difficult to see. It is like trying to study a candlelit room while someone shines a searchlight through the window. This is especially true at high energies. Blazars are major sources of gamma rays, the most energetic kind of light. Gamma rays are not something our eyes can see, and Earth's atmosphere blocks most of them before they reach the ground, which is very considerate of the atmosphere, really. To study them, astronomers often use space telescopes, such as NASA's Fermi Gamma Ray Space Telescope, which watches the high-energy sky. In ordinary visible light, the night sky may seem calm, with stars shining steadily. But in gamma rays, the sky becomes far more active, and blazars are among the objects that stand out. Gamma rays tell us that the particles in blazar jets are being accelerated to extraordinary energies. Electrons and possibly protons are moving through magnetic fields, colliding with photons, spiraling, scattering, and releasing radiation. The details can become complex very quickly, but the broad picture is clear. A blazar jet is a natural particle accelerator. It takes matter and energy near a supermassive black hole and turns part of it into a narrow, fast-moving stream that can shine across the universe. Even radio waves from blazars can be intense. Radio telescopes often reveal compact cores and jets that appear to change position over time. Sometimes parts of these jets seem to move faster than light across the sky. This does not mean anything is actually breaking the cosmic speed limit. The apparent faster-than-light motion is another effect of geometry and relativity. When a jet moves nearly at light speed and almost directly toward us, the light from later positions has a shorter distance to travel, which can make the motion appear exaggerated. The result is called superluminal motion. It sounds illegal, as if the jet has been pulled over by the physics police, but the laws of relativity remain safe and intact. This is one reason blazars are so useful for testing our understanding of high-speed astrophysics. They force us to take relativity seriously. They are not objects we can fully explain with slow, comfortable intuition. We have to remember that light takes time to travel, that motion changes what we see, and that direction matters. The universe at near-light speed is not the universe of rolling balls and drifting clouds. It is a place where time, brightness, and apparent motion can all shift depending on how the source moves and where the observer sits. Blazars also earn their reputation as beacons because they can vary so quickly. Some astronomical objects change over thousands or millions of years, which is not always convenient for a species that struggles to wait for a kettle. But blazars can flare on human timescales. A blazar that looks relatively quiet can brighten dramatically, sometimes in days, hours, or even less. That rapid variability tells astronomers something about the size of the region producing the light. If an object changes very quickly, the emitting region cannot be enormous, because information cannot travel across it faster than light. A sudden brightening suggests that a relatively compact part of the jet has become active. This is surprising when we remember the scale of the central black hole. We're talking about a system involving a black hole millions or billions of times the mass of the Sun, a disk of hot gas, magnetic fields and jets that can stretch far beyond the galaxy. Yet some of the most dramatic changes may come from regions small enough, in cosmic terms, to flicker quickly. It is a little like seeing an entire city brighten because one engine in the centre suddenly roared to life. The scale is huge, but the signal can be sharp. Astronomers monitor blazars because these flares can reveal how jets work. A brightening in visible light might be followed by a change in radio waves. A gamma-ray flare may appear alongside X-ray activity. Sometimes the timing lines up neatly, and sometimes it does not. That is part of the challenge. The jet is not a simple tube with a single glowing bulb inside. It may contain shocks, knots, turbulent regions, magnetic reconnection events, and zones where particles are energized in bursts. We can say jet as if it is one thing, but inside it, many processes may be taking place at once. A helpful way to picture it is to imagine a fast river, though we should be careful, because this river is made of plasma and magnetic fields rather than water. Some parts flow smoothly, other parts are choppy. There may be narrow channels, sudden compressions, swirling regions, and places where energy is released quickly. If sunlight were reflecting from the river, it would not shine evenly. It would flash, sparkle, dim and brighten as the surface changed. A blazar jet, in a much more extreme way, can produce changing light because the conditions inside the jet keep changing. Another reason blazars matter is that they can be seen across enormous distances. A bright blazar can act like a marker in the remote universe. Its light travels through the space between galaxies, and along the way it can interact with material and radiation in that space. By studying how blazar light is altered during its journey, astronomers can learn not only about the blazar itself, but also about the universe between the blazar and us. The beacon illuminates more than its own source. It gives clues about the cosmic background light, intergalactic magnetic fields, and the history of energetic processes over time. This is one of those details that makes astronomy feel like detective work carried out with light. We cannot visit a blazar, we cannot take a sample of its jet and place it gently into a laboratory jar, which is probably for the best. Instead, we receive light. That light contains patterns. Its brightness, colour, energy, timing and polarization all carry information. When astronomers analyse those patterns, they are reading the record of a distant engine and the path the signal took to reach us. The blazar becomes both a subject and a tool. It is something we study, and something we use to study other things. The brightness of blazars also raises a natural question. If they are so powerful, should we be worried about them? The comforting answer is no, not in the ordinary sense. Blazars are far away, usually far beyond our galaxy. Their light reaches us after spreading across huge distances, and the high-energy photons that arrive are detected by instruments, not felt as danger in daily life. A nearby jet pointed directly at Earth could be a serious matter, but the blazars we observe are remote cosmic objects, not immediate threats. They are more like distant thunderstorms seen from the safety of a warm room. Powerful, fascinating, and best appreciated through a very good window. There is something restful about that distance. The same universe that contains such violent engines also gives us enough space to observe them calmly. Here on Earth, we can sit in a quiet room and think about a black hole launching a jet across intergalactic space. We can study gamma rays, radio waves, and X-rays without leaving our planet. We can build instruments, compare data, and slowly piece together the behavior of an object so energetic that it can outshine its own galaxy. Astronomy turns distance into knowledge. It takes what is unreachable and makes it understandable, at least bit by bit. Of course, the word brightest can mean different things depending on how we measure. A blazar may be especially bright in gamma rays, radio waves, or across its overall energy output. Some blazars flare dramatically for short periods, becoming temporary record holders in one part of the sky. Others remain steady enough to serve as reliable reference sources. Brightness also depends on distance. An object can be intrinsically powerful but appear faint because it is far away, while a less powerful object nearby may look brighter from Earth. So when we call blazars bright beacons, we're usually speaking about a combination of intrinsic power, relativistic boosting, and detectability across cosmic distance. That combination is what makes them special. A normal star shines because nuclear fusion in its core produces light and heat. A galaxy shines because it contains many stars. A blazar shines because matter falling toward a supermassive black hole releases gravitational energy, and part of that energy is organized into a jet that points nearly at us. This is a different kind of brightness. It is not steady like a calm star. It is not spread out like a galaxy's starlight. It is concentrated, variable, boosted, and tied to some of the strongest gravity and fastest motion in the universe. At the center of this brightness is a strange partnership between darkness and light. The black hole itself emits no light from within its event horizon. That boundary remains dark, but the environment around it can be brilliant. Gas heats as it falls inward. Magnetic fields extract and guide energy. Jets carry that energy outward. So the black hole, famous for being dark, becomes associated with one of the brightest phenomena we can see. This is not really a contradiction. It is a reminder that black holes are not isolated holes in space. They are part of systems. What happens around them can be just as important as what happens inside the boundary we cannot see. As we follow the beam back toward its source, the picture becomes more detailed. The brightness we observe is not produced by a simple lamp at the center of a galaxy. It comes from a chain of events. Gas must be available near the black hole. It must form an accretion disk. Magnetic fields must organize and strengthen. The black hole's spin may help power the jet. Particles must be accelerated. Radiation must be produced, boosted, and aimed. Then, after all that, the light must cross the universe and reach our instruments. A blazar looks like a point in the sky, but behind that point is an entire machine. For now, we can rest with this idea. Blazars are among the brightest beacons in the deep universe because they combine enormous energy with a narrow aim. They are active galaxies viewed from a special angle, where one relativistic jet points almost toward us. Their brightness is intensified by speed, direction, and the extreme physics around a supermassive black hole. They flare, flicker, and shine across many kinds of light, from radio waves to gamma rays, and because of that, they allow us to study the universe at energies and distances that would otherwise remain hidden. Before we can understand the beam of a blazar, we have to remember that it does not come from nowhere. It is not a lonely torch drifting through space, and it is not just a black hole shining by itself in the dark. A blazar belongs to a galaxy. Around the bright center there may be billions, sometimes hundreds of billions of stars. There may be clouds of gas, lanes of dust, older star clusters, younger regions where new stars are forming, and a long history of collisions, mergers, quiet periods, and active phases. The blazar is the loudest thing we notice, but it is sitting inside a much larger system. It is the restless heart of a galaxy that, from far away, may look like a single point of light. That is one of the first strange things about these objects. When we look across deep space, we're often seeing the center more easily than the galaxy around it. The active core can be so bright that the ordinary starlight of the host galaxy is partly hidden, as if someone placed a brilliant lamp in the middle of a town, and then asks you to study the rooftops around it. The town is still there. The streets, houses and trees have not disappeared. But the lamp overwhelms your view. In the same way, a blazar's central engine can dominate the light we receive, making the galaxy that holds it difficult to separate from the glare. Most large galaxies are thought to contain supermassive black holes at their centres. Our own Milky Way has one called Sagittarius, a star, with a mass of about 4 million suns. That sounds enormous, and it is, but compared with some black holes in active galaxies, it is not especially large. Some central black holes weigh hundreds of millions or billions of solar masses, yet mass alone does not decide whether a galaxy becomes active. A black hole can be huge and still quiet if there is not much nearby material falling into it. The important question is not only how big the black hole is, but whether it is being fed. A quiet central black hole is a bit like a fireplace with no wood on it. The fireplace can be large, heavy and ready, but if nothing is burning, the room stays dark. In an active galaxy, material is available. Gas and dust have found their way toward the centre. Maybe the galaxy has recently merged with another galaxy. Maybe gravitational interactions have disturbed clouds of gas and sent them inward. Maybe the galaxy's own structure has slowly guided material down toward the middle over long periods of time. However it happens, the result is that the black hole is no longer simply sitting in the dark. It has fuel around it. That fuel does not fall straight in. Space near a black hole is not like a smooth hole in the floor where everything drops vertically. Gas usually has angular momentum, which means it is moving sideways as well as inward. Because of that motion, it forms a disk around the black hole, called an accretion disk. This disk can become extremely hot as material rubs, compresses and spirals closer to the centre. Friction, turbulence and magnetic effects turn gravitational energy into radiation. Matter falling inward loses energy, and that lost energy escapes as light. In some active galaxies, this disk glows so intensely that it can outshine all the stars in the surrounding galaxy. A blazar is connected to this active central region, but it is not defined only by the disk. The defining feature is the jet. The galaxy has a central black hole that is feeding, an accretion disk that is glowing, and jets launch from the region close to the black hole. When one of those jets points almost directly toward us, we see the object as a blazar. So the restless heart is not simply bright because material is falling inward. It is bright because the system is also throwing energy outward in a highly organised, narrow relativistic stream. This can feel backwards at first. A black hole is famous for pulling things in. It is the object in the universe most associated with no escape. Yet some of the most dramatic black hole systems are also connected with jets that extend far beyond the central region. The important point is that the jet is not escaping from inside the event horizon. Nothing does that. The jet forms outside that boundary, in the crowded, magnetised, fast-moving environment where the accretion disk, black hole spin and magnetic fields interact. The black hole is not shining from within. The activity around it is doing the work. If the galaxy is the body, the active nucleus is the heart, though perhaps a heart that has had far too much coffee. It does not beat gently. It flickers, flares, feeds, and launches. It changes in brightness. It sends energy into space. It can influence the gas around it and even affect the future growth of the host galaxy. This is one reason active galactic nuclei matter so much in astronomy. They are not just exotic objects placed in galaxies like decorations. They can help regulate the galaxies they live in. That influence is sometimes called feedback. It means energy from the active centre flows back into the surrounding galaxy and changes what happens there. Jets can push into gas. Winds can drive material outward. Radiation can heat nearby clouds. In some cases, this activity may slow down star formation by heating or removing the cold gas that would otherwise collapse into new stars. In other cases, shocks from jets may compress gas and help trigger star formation in certain regions. The details depend on the galaxy, the jet, the gas, and the timing. The active centre is not just a small bright dot. It can be a major part of how the galaxy evolves. This gives a blazar a broader story. It is not only a beam pointed toward Earth, it is the visible sign of a galaxy undergoing central activity. The light we see has passed through layers of context. First, a galaxy formed and grew. It collected stars and gas. Its central black hole grew as well, likely through accretion and mergers over cosmic time. At some point, enough material reached the centre to power an active nucleus. The disk heated. Magnetic fields became important. Jets formed. One jet happened to point near our direction. After that, light from the system crossed the universe and entered our telescopes. The blazar is what that entire chain looks like from our angle. Many blazars are found in large elliptical galaxies. Elliptical galaxies are often older systems, with smooth shapes and less obvious spiral structure than galaxies like the Milky Way. They can form through mergers, when smaller galaxies collide and combine. Such mergers are messy but very effective at moving gas around. During a merger, gravitational forces disturb the orbits of stars and gas clouds. Gas can lose angular momentum and flow inward toward the centre. That inward flow can feed the central black hole and help awaken an active nucleus. Not every merger makes a blazar, of course. The universe is rarely that simple, but galaxy interactions are one important way to supply black holes with fuel. Even in calmer times, a galaxy centre is not a simple place. Stars orbit in dense swarms, gas clouds move under gravity, dust blocks and reddens light. Magnetic fields thread through plasma. Near the black hole, the speeds become higher, the temperatures rise, and the physics grows more extreme. A small amount of matter falling into a supermassive black hole can release a huge amount of energy because gravity near the black hole is so strong. Compared with ordinary nuclear fusion in stars, accretion onto a black hole can be remarkably efficient at turning mass into radiation. That is why a region not much larger than a solar system in some cases can outshine a galaxy. This is worth holding carefully. The galaxy may contain hundreds of billions of stars spread across tens or hundreds of thousands of light years. Yet the central active region, tiny by galactic standards, can dominate the light we observe. That does not mean it contains more matter than the galaxy. It means the energy released per unit mass is extraordinary. Matter near the black hole is not just warm. It can be heated to temperatures that produce ultraviolet light, X-rays and other high-energy radiation. Then, in blazars, the jet adds another layer, producing radio waves, visible light, X-rays, and gamma rays through processes linked to fast particles and magnetic fields. A useful way to imagine the host galaxy is as a vast, mostly quiet city at night. Most windows glow gently. Streets curve across large distances. Some neighbourhoods are old and calm. Some regions may still be building new stars, like lights turning on in new houses. At the centre, however, there is an engine room. It is compact, loud, and bright. The rest of the city may be beautiful, but the engine room is where the extreme activity is happening. In a blazar, one powerful beam from that engine room happens to point nearly toward our street. Because the central light is so strong, studying the host galaxy can be difficult. Astronomers often need careful observations to subtract the glare of the active nucleus and reveal the surrounding stars. Different wavelengths help. Infrared light can sometimes show the host galaxy more clearly, because dust and central glare affect it differently than visible light. High-resolution imaging can separate structures that would otherwise blend together. Spectroscopy can identify the signatures of stars, gas, and the active nucleus. Little by little, astronomers can pull the galaxy back out from behind its own brilliant centre. That work matters because the host galaxy can tell us why the blazar exists. The mass of the central black hole, the amount of available gas, the age and structure of the galaxy, and its merger history all help shape the activity. The jet may be the most noticeable feature, but it depends on the conditions near the black hole, and those conditions are connected to the galaxy's wider life. The heart is restless for a reason. Something is feeding it. Something has arranged the environment so that energy can be released and directed outward. There is also a deep connection between supermassive black holes and the galaxies around them. Astronomers have found relationships between the mass of central black holes and properties of the galactic bulge, the dense central region of stars in many galaxies. This suggests that black holes and galaxies grow together, or at least influence one another over time. The black hole is not an unrelated object dropped into the centre. It is part of the galaxy's history. It grows when material reaches it. Its activity can affect the galaxy's gas. The galaxy shapes the supply of fuel, and the black hole shapes the environment in return. In a blazar, we are seeing that relationship during an especially dramatic phase, and from an especially dramatic angle. If we could move far to the side of the same object, away from the line of the jet, it might not look like a blazar anymore. It might look like another kind of active galaxy. The same restless heart would still be there, but the appearance would change. This is an important lesson. The categories astronomers use are partly about the object itself, and partly about our viewing direction. A blazar is not just a thing. It is a thing seen from a particular line of sight. That can make the universe feel almost conversational, though not in any mystical sense. The object sends light in all sorts of forms, but the message we receive depends on where we are sitting. From Earth, the jet is nearly face-on. From somewhere else, far across the cosmos, the same galaxy might look less intense, or its extended radio lobes might stand out more clearly, or the central glare might be partly hidden by dust. No observer sees everything. Each view is one slice of the full system. Astronomy is the art of learning the whole object from one slice at a time. The restless heart of a blazar also changes with time. It is not a steady machine running at one unchanging setting. The supply of gas can vary. Conditions in the disk can shift. Magnetic fields can rearrange. Shocks can move through the jet. Bright knots can appear and fade. Flares may occur when particles are rapidly accelerated or when regions inside the jet collide. From our point of view, these changes can appear as sudden increases in brightness. The galaxy's centre is alive with activity. Not alive biologically, of course, but active in the physical sense. It is a system far from stillness. Some blazars flare so strongly that astronomers across the world turn their instruments toward them. A gamma-ray telescope may notice an outburst. Optical observers may begin monitoring it. Radio telescopes may watch for changes in the jet. X-ray telescopes may add another part of the picture. The object becomes a temporary focus of many eyes. This is because each flare is a clue. It can tell us about the size of the emitting region, the energy of the particles, the magnetic field, the structure of the jet, and the connection between the disk and the beam. The restless heart reveals itself through change. Still, from the point of view of ordinary human life, all of this remains beautifully distant. The galaxy may be billions of light years away. Its central black hole may be feeding with enormous power. Its jet may be racing toward us in a narrow cone of radiation. And yet, here, the result is a measurement. A curve on a graph. A photon counted by a detector. A faint source in a telescope's field. The violence is real, but it arrives as information. That is one of the calming contradictions of deep space astronomy. The universe can be extreme without being immediate. It can be dramatic without being noisy. It can contain engines of almost unbelievable power, and still we meet them in silence. Imagine the host galaxy again, but now not as a still picture. Let it move through cosmic time. Stars are born, age, and die. Supernovae enrich the gas with heavier elements. Smaller galaxies fall in and merge. Gas drifts inward after disturbances. The central black hole grows in short feeding episodes separated by quieter spans. Sometimes the nucleus brightens. Sometimes the jet strengthens. Sometimes the activity fades as the available fuel runs low or is pushed away. A blazar may not remain a blazar forever in the same visible state. It is a phase, an angle, a behaviour, and a moment in the long life of a galaxy. This helps prevent a common misunderstanding. A galaxy with a blazar is not necessarily exploding, and the black hole is not swallowing the entire galaxy. The stars in the host galaxy are mostly far too distant from the central black hole to fall in. They orbit under the combined gravity of the galaxy as a whole. The black hole dominates only the central region. Even a supermassive black hole is small compared with the scale of its galaxy. It may have enormous mass, but the galaxy is enormous in size. The active nucleus is powerful because matter near the centre releases energy efficiently, not because the entire galaxy is being consumed at once. That is reassuring, and it also makes the physics more interesting. The black hole does not need to eat the galaxy to shine. It only needs a supply of material reaching the inner regions. A relatively modest amount of gas compared with the mass of the whole galaxy can power tremendous radiation if it falls deep into the black hole's gravitational well. The disk and jet turn local feeding into cosmic visibility. The host galaxy provides the setting and the fuel. The central engine transforms that fuel into light and motion. A blazar's restless heart may also help explain why some galaxies stop forming many new stars. In large galaxies, especially massive ellipticals, star formation can become weak because cold gas is used up, heated, or expelled. Active nuclei are one possible part of that story. Jets can inflate bubbles in hot gas around galaxies and galaxy clusters. Energy from the centre can keep gas from cooling efficiently. Without enough cold gas, fewer new stars form. This process is still an active area of research, and not every detail is settled, but the broad idea is important. Black holes, despite being compact, can influence regions far larger than themselves. That influence makes active galaxies more than curiosities. They are part of cosmic history. When the universe was younger, galaxies had more gas, mergers were more common, and supermassive black holes were growing rapidly. Active galactic nuclei were more common then than they are today. Blazars, especially distant ones, can therefore serve as signposts of an era when massive black holes and galaxies were building themselves more vigorously. Looking at a distant blazar is not only seeing a bright object, it is seeing a galaxy in a younger universe, when the central engine had enough fuel and structure to send a beam across time. This gives the host galaxy a kind of quiet importance. The jet gets the attention, but the galaxy holds the history. It contains the stars that form before the flare, the gas that may feed the disk, the gravitational environment that shaped the black hole's growth, and the marks of past interactions. If the blazar is the lighthouse beam, the host galaxy is the island, the cliff, the weather, the old stone foundation, and the long record of why the light is there at all. Without the galaxy, there is no central black hole with a history. Without the fuel, there is no active disk. Without the disk and magnetic fields, there is no jet. Without the alignment, there is no blazar as we see it. So when we say a blazar is a galaxy with a restless heart, we are being more literal than it first sounds. The heart is the active nucleus, the region around a feeding supermassive black hole. It is restless because matter is moving inward, energy is being released, fields are changing, and jets are carrying power outward. The galaxy around it may be old and quiet in its stars, or shaped by past mergers, or still holding enough gas to feed the centre. The bright point we observe is therefore not a simple object. It is a relationship between a black hole, a disk, a jet, a galaxy, and our viewing angle. From here, the path inward becomes unavoidable. We have looked at the blazar as a beacon, and then as the active centre of a galaxy. Now, the most important question waits at the core. What kind of black hole can power such a system? How does something that does not let light escape become connected to a beam bright enough to cross the visible universe? At the centre of all this brightness sits something that, by itself, gives off no light at all. That is the strange little twist we have to hold carefully. The beam of a blazar can shine across billions of light years. It can flood telescopes with radio waves, visible light, X-rays and gamma rays. It can flare, fade and brighten again like some restless signal from the edge of the observable universe. And yet the object behind the whole performance is a black hole, a place where light, once it crosses the boundary, cannot return. The brightest beacon begins with the darkest centre. That sounds almost like a contradiction, but it is really a matter of location. The black hole itself is not glowing. Nothing from inside the event horizon escapes to announce itself. The light comes from the region around it, where gas, dust, plasma, magnetic fields and gravity are crowded into one of the most extreme environments nature can make. If you imagine the black hole as the silent centre of a storm, the storm is what we see. The winds, the heat, the charged particles, the disk, the jet, the changing light, all of that happens outside the point of no return. The black hole anchors the system, but the surroundings do the shining. A supermassive black hole is not just a heavier version of a star-sized black hole. It is a different scale of object altogether. Stellar black holes may have masses of a few times the Sun, or perhaps tens of solar masses. Supermassive black holes live in the centres of galaxies and can weigh millions or billions of times more than the Sun. Some may be even heavier. They are not large in the way a galaxy is large, spread out across unimaginable distance. They are compact for their mass, packed into a region where gravity becomes severe enough to reshape the paths of light, matter, and time. The black hole at the centre of our Milky Way, Sagittarius A star, is already a remarkable object, with a mass of about 4 million suns, yet it is fairly calm today. It is not swallowing huge amounts of material, and it is not producing a blazar jet aimed at us. A blazar's black hole is usually much more active. It has a supply of matter falling toward it. It may also be spinning rapidly, and that spin may matter for the power of the jet. The exact details are still an active area of research, but astronomers know that the most powerful jets are connected to feeding black holes surrounded by magnetized material. Feeding is the important word here, though it can create the wrong picture if we are not careful. A black hole does not roam through its galaxy like a vacuum cleaner, chasing stars and gulping them down. Most stars in a galaxy are far too far away to be directly affected by the central black hole in that dramatic way. They orbit within the gravitational field of the galaxy as a whole. The black hole dominates only the innermost region. For it to become active, material has to lose enough angular momentum to move inward. Gas must find its way toward the centre, often after a disturbance, a merger, or slow gravitational processes within the galaxy. Once gas approaches the black hole, it usually forms an accretion disk. This disk is one of the main reasons active galactic nuclei can become so bright. The gas in the disk is not calmly circling like a row of polite cars around a roundabout. It is turbulent, hot, compressed, and moving at tremendous speeds. Inner material orbits faster than outer material. Layers rub, twist, and exchange energy. Magnetic fields thread through the plasma. The gas heats up and radiates. The closer it moves to the black hole, the more gravitational energy it can release. This is why black holes can power such luminous systems. The energy does not come from the black hole shining like a star. It comes from matter falling into a deep gravitational well. When matter falls toward a massive object, it loses gravitational potential energy. Around a black hole, the well is very deep, so the energy release can be enormous. A small amount of matter, by cosmic standards, can produce astonishing radiation as it spirals inward. In this sense, an active black hole is not a furnace in the ordinary way. It is a conversion machine, turning the energy of falling matter into heat, light, motion, and sometimes jets. There is a boundary around every black hole called the event horizon. This is not a solid surface. If you were unlucky enough to fall toward one, you would not hit a shell or wall at the horizon. Instead, it marks the region where escape becomes impossible. Outside the event horizon, light can still travel away if it is moving in the right direction. Inside it, all paths lead inward. The event horizon is the point where the black hole becomes truly black to the outside universe. For a non-spinning black hole, the size of this boundary depends on mass. For a supermassive black hole, the horizon may be large enough to fit entire planetary systems across, yet still tiny compared with the galaxy around it. Near that boundary, space and time are strongly curved. Matter moving close to the black hole orbits at a huge fraction of the speed of light. Radiation can be bent, light can loop around. A distant observer may see strange distortions, because the black hole's gravity changes the paths photons take. But in a blazar, we are usually not directly seeing the event horizon itself. We are seeing the output of the system around it, especially the jet. The black hole is the reason the system can become extreme, but the jet is the reason the object becomes a blazar from our point of view. The accretion disk matters because it supplies energy and structure. But the jet seems to depend strongly on magnetic fields as well. Near a feeding black hole, the gas is not neutral, quiet, and simple. It is plasma, meaning electrons and ions are separated enough to respond strongly to electromagnetic forces. Magnetic fields can become wound up by the rotation of the disk, and possibly by the rotation of the black hole itself. When these fields become organized on large scales, they can help launch and guide narrow outflows away from the central region. A useful way to picture magnetic fields here is not as rigid wires, but as flexible lines of influence threaded through moving plasma. As the disk rotates, those field lines can twist. Charged particles follow and interact with them. Under the right conditions, energy can be channeled away from the black hole and disk in two opposite directions, roughly perpendicular to the disk. The result is a pair of jets. One points one way, the other points the opposite way. Most of the time we see active galaxies from some side angle. With a blazar, one of those jets is aimed nearly toward us, and that one-sided view changes everything. The black hole's spin may be especially important. A spinning black hole is not just sitting there in space, it drags the surrounding space-time around with it, an effect called frame dragging. Near a rapidly rotating black hole, the environment is different from the environment around a non-spinning one. In some models, energy can be extracted from the spin of the black hole through magnetic fields. This is often discussed in connection with powerful relativistic jets. The full physics is complex, and scientists continue to study how jet launching really works, but the broad idea is clear enough for our quiet purposes. A feeding black hole, a magnetized disk, and rapid rotation can create conditions where energy is driven outward in narrow beams. That idea also helps explain why not every supermassive black hole produces a visible jet. Many galaxies have central black holes. Many black holes may occasionally feed, but strong jets seem to require particular conditions. The disk must be arranged in the right way. Magnetic fields must be strong and organized enough. The black hole's spin may need to contribute. The surrounding environment must allow the outflow to escape. A blazar is therefore not just a supermassive black hole with a snack. It is a full engine, with fuel, rotation, magnetic structure, and an angle that points its most dramatic feature toward us. The word engine is useful, but only if we remember that there are no pistons, no metal chambers, and no friendly mechanic leaning over with a wrench. The parts are physical processes. Gravity pulls matter inward. Rotation forms a disk. Friction and turbulence heat the gas. Magnetic fields store and transfer energy. Particles accelerate. Radiation forms. Jets carry energy outward. The black hole does not need machinery in the human sense. It has nature's own version, built from gravity and electromagnetism, and it runs on scales that make even our largest machines seem like table toys. The scale is difficult to picture, so we can approach it gently. The central black hole might have a mass of hundreds of millions of suns. The accretion disk may span a region comparable to the size of a solar system, or larger, depending on how we define the emitting zones. The jet can extend far beyond the central galaxy, sometimes reaching across hundreds of thousands of light years or more. The region launching the jet may be compact, but the result can influence enormous distances. It is as if a small valve at the centre of a city could send a narrow beam across a continent, except the city is a galaxy, and the continent is intergalactic space. This is why the supermassive black hole behind a blazar is both small and huge, depending on what we mean. Its event horizon is small compared with the galaxy. Even a massive black hole is tiny next to a 100,000 light-year-wide system of stars. But in terms of influence, the black hole can be enormous. Through accretion, radiation, winds, and jets, it can affect gas far beyond its immediate neighbourhood. It can help shape the galaxy's future. It can send signals across the universe. It is compact in size but not compact in importance. There is another idea that helps keep the black hole's role clear. A black hole does not need to be actively consuming matter at a huge rate forever. Activity can come and go. A galaxy's centre may be quiet for long periods, then brighten when new material reaches the inner disk. The black hole may go through feeding episodes. During one episode, it may produce strong radiation and jets. Later, when the fuel supply changes, it may fade. So a blazar is not necessarily a permanent identity written into the galaxy forever. It is a phase we observe, shaped by activity and alignment. This also means the black hole has a history. It did not appear fully grown in one instant. Supermassive black holes grow over cosmic time by accreting gas and merging with other black holes when galaxies collide. In the early universe, some grew very quickly, becoming enormous while the cosmos was still young. That remains one of the important puzzles in astrophysics. How did some black holes become so massive so soon? Distant blazars may help with this question, because they can reveal powerful black holes at great distances, where we are seeing the universe as it was long ago. Their beams make them easier to detect across cosmic time, so they can serve as signposts of early black hole growth. Still, even a supermassive black hole cannot shine without surroundings. If the region around it were empty, it would be nearly invisible except through its gravity. It needs material to reveal itself. This is a useful reminder about black holes in general. They are often discussed as if they are cosmic monsters, but an isolated black hole can be quiet and hard to find. It is the material around a black hole that makes the show. Gas falling in, stars orbiting nearby, disks heating up, jets launching. These are the clues. The black hole's darkness is made visible by what it does to other things. In the case of a blazar, the jet is the most dramatic clue. It tells us that the central region is not merely feeding, but organising energy into an outgoing flow. The particles in the jet move at relativistic speeds, meaning close enough to the speed of light that Einstein's physics becomes essential. Because the jet points nearly toward us, its radiation is boosted. That is why the black hole behind the beam can seem brighter than the galaxy around it. The black hole itself remains dark, but its environment becomes one of the most luminous engines in the universe. This is not the same as a black hole exploding. It is not a blast from inside the event horizon. It is a sustained or repeated outflow generated by the conditions outside the black hole. That difference matters because it keeps the picture physically sensible. The event horizon still traps light. Relativity still holds. The black hole is not leaking. Instead, the disk and magnetic fields near it are launching some matter and energy away before it crosses the boundary. Some gas falls in, some energy radiates away, some material may be driven outward. The central engine is not a one-way drain. It is a complex environment where different paths are possible until the event horizon is crossed. If we could somehow hover safely near a blazar's central region, which we absolutely could not, the view would not resemble a peaceful dark sphere with a neat glowing ring around it. It would be dangerous, bright and chaotic. The disk would blaze. High-energy radiation would fill the region. Magnetic fields would shape streams of charged particles. The jet would erupt along the axis, narrow near the base and spreading or interacting with its environment farther out. Time itself would run differently near the black hole than it does far away, because strong gravity affects the passage of time. Every simple description becomes a simplification. From Earth, though, we do not need to endure any of that. We receive the signals after their long journey. A gamma-ray photon, an X-ray photon, a radio wave, each carries part of the story. The rapid flickering tells us about compact regions and fast processes. The spectrum tells us about the energies of particles and the mechanisms producing radiation. Polarization can reveal magnetic field structure. Changes in brightness over time can suggest shocks, turbulence, or fresh injections of particles into the jet. The black hole is hidden, but the behavior of the light around it becomes a kind of indirect portrait. Astronomers have become very skilled at reading these portraits. They can estimate black hole masses using the motion of gas or stars, or through relationships involving the host galaxy and emission lines. They can model accretion disks and jet spectra. They can compare the timing of flares in different wavelengths. They can use very long baseline radio interferometry to see fine jet structures on tiny angular scales. They cannot place a ruler beside the black hole, of course, but they can combine many kinds of evidence, and from that evidence, build a working picture of the central engine. There is humility in that method. We do not see the supermassive black hole directly in the ordinary sense. We infer it from gravity, motion, radiation, and structure. In a few nearby cases, such as the black hole in the galaxy, M87, astronomers have imaged the shadow-like region created by light bending around the black hole. But most blazars are far too distant for that kind of direct imaging. Their central black holes are known through their effects. The beam itself becomes one of the strongest witnesses. It says in its own energetic way that something massive, compact and powerful is operating at the galaxy's centre. The black hole also gives us a way to think about energy more broadly. On Earth, we often think of energy as something produced by burning fuel, splitting atoms, or capturing sunlight. Around a supermassive black hole, gravity becomes the main source. Matter falling inward can release energy with extraordinary efficiency. If the black hole is spinning and threaded by magnetic fields, even rotational energy may become part of the power source for jets. This does not make black holes magical. It makes them excellent at turning motion and gravity into radiation and outflow. That is why the black hole behind the beam is not simply a background detail. It is the central reason a blazar can exist. Without the supermassive black hole, there is no deep gravitational well. Without the accretion disk, there is no intense release of energy from falling matter. Without magnetic fields and rotation, there may be no strong relativistic jet. Without the jet aimed nearly toward us, the object would not appear as a blazar. Each part depends on the others. The beam is not separate from the black hole. It is the outward expression of the black hole's environment. This also helps explain why blazars can feel so extreme, but still belong within the same universe as everything else. They are governed by the same physical laws as falling apples, orbiting planets, and electric currents. Gravity, motion, radiation, and magnetism are familiar ideas, but in a blazar they are turned up to settings we never meet in daily life. The difference is scale and intensity. The same universe that lets a compass needle respond to a magnetic field also lets magnetic fields near a black hole help guide plasma into a jet. The same gravity that keeps your feet on the ground can, in a far stronger form, power a disk bright enough to be seen across cosmic history. So the supermassive black hole behind a blazar is not just a dark object hiding behind a bright beam. It is the source of the conditions that make the beam possible. It is massive enough to dominate the centre of a galaxy, compact enough to create extreme gravity, and often active enough to be surrounded by a hot accretion disk. Its spin and magnetic environment may help launch jets that race outward at nearly light speed. And when one of those jets points toward us, the hidden centre announces itself across the universe. That brings us to the next question waiting inside the beam. How does something so narrow stay organised across such large distances? How do particles escape the crowded region near the black hole and travel outward so quickly? And why does the jet produce light from radio waves all the way up to gamma rays? Getting a jet out of a black hole system sounds, at first, like asking smoke to escape from a sealed room. The name black hole seems to promise that everything goes in and nothing comes back. Light cannot escape from inside the event horizon. Matter cannot turn around after crossing that boundary. Even the fastest signal in the universe has no outward path once it has gone too far. So when we say that a blazar has a jet, and that this jet comes from the region around a supermassive black hole, it is worth slowing down and being very clear. The jet does not escape from inside the black hole. It forms outside it, in the crowded, heated, magnetized space where matter is still fighting, spiraling, glowing, and not quite lost. That difference is the key that opens the whole idea. A black hole is not a solid object with a surface that spits things out. It is a region of space-time with a boundary. Outside that boundary, physics is extreme but not hopeless. Matter can still orbit. Light can still travel away, if it is headed in the right direction. Magnetic fields can still twist through hot plasma. Gas can still heat and shine. Some material continues inward and eventually crosses the event horizon. Some of it releases energy before that happens. And under the right conditions, a fraction of the system's energy is redirected outward, not as a gentle breeze, but as a narrow jet moving at nearly the speed of light. Think of the central region as a very busy roundabout, though perhaps one designed by a committee of gravity, magnetism, and poor sleep habits. Gas does not fall straight into the black hole like sand dropping through a hole in a bag. It has sideways motion, so it circles. As it circles, it forms a disk. The inner parts of that disk orbit faster than the outer parts, which means the material is constantly shearing past itself. The gas becomes hot. The atoms become stripped into charged particles. The whole disk becomes plasma, a state of matter that responds strongly to electric and magnetic fields. This plasma is not simply glowing. It is moving, twisting, dragging magnetic fields with it, and feeding the central engine. The accretion disk is where a great deal of the visible and invisible activity begins. In a quiet galaxy, the central black hole may have little gas around it, and therefore little to reveal its presence. In a blazar, the black hole is actively fed. Matter spirals inward, heats up, and releases radiation. The disk can shine in ultraviolet light, visible light, and X-rays depending on its temperature and structure. But the jet is a different piece of the system. It is not just the disk glowing. It is an outflow, a stream of particles and energy channeled away from the black hole's surroundings along the system's rotation axis. Why should anything be launched outward at all? The answer appears to involve magnetic fields. Near a feeding black hole, magnetic fields can become extremely strong and organised. Plasma is full of charged particles, and charged particles do not ignore magnetic fields. They spiral around field lines. They help carry the fields along. They transfer energy through them. As the disk rotates, it can wind magnetic fields into twisted shapes. If the black hole itself is spinning, it can also affect the surrounding space-time and may help supply energy to the system. The result in simplified form is that magnetic fields can act like channels, guiding some material and energy away from the centre instead of letting everything fall inward. A useful image is a spinning garden sprinkler, though we must immediately make it less garden-like and much more alarming. Water enters the middle, pressure builds, and streams shoot outward along fixed paths. Around a black hole, there is no garden hose, no metal nozzle, and no kindly person in sandals adjusting the flow. Instead, there is gas falling inward, a disk rotating at high speed, magnetic fields wound into structure, and a central object so dense that space-time itself is strongly curved. The jet is not sprayed out by pressure alone. It is launched by a combination of rotation, magnetism, and energy extraction from the region around the black hole. One leading idea is that magnetic fields anchored in the accretion disk can fling material outward, a little like a bead sliding along a rotating wire. If the field line rotates and the plasma is tied to it, the plasma can be accelerated away from the disk. Another important idea is that magnetic fields near a spinning black hole can tap some of the black hole's rotational energy. In that view, the black hole's spin helps power the jet through electromagnetic processes outside the event horizon. The full details are not settled in every case, and real jets may involve more than one mechanism. But the overall story is clear enough. Jets are not leaks from the black hole. They are products of the black hole's environment. This is why the word escape needs care. Nothing escapes from inside the event horizon, but plenty can escape from just outside it if it has not yet crossed the boundary and if it gains the right kind of energy. The jet is made of particles and radiation that were part of the black hole's surroundings, not prisoners released from the inside. It is more like sparks thrown up from a forge than objects climbing back out of a locked cellar. The forge is hot because material is falling into a deep gravitational well. The sparks fly because the environment around that fall is turbulent, magnetized, and rotating. Once the jet begins, it has to remain narrow. That is another remarkable part of the story. A blazar jet can travel far beyond the central region of its galaxy. Some relativistic jets extend for thousands, even hundreds of thousands of light years, and in some systems their influence reaches still farther through surrounding gas. How does something launched from near a black hole keep its direction over such distances? Again, magnetic fields are central to the answer. They help collimate the flow, which means they keep it focused into a narrow beam rather than letting it spread out in every direction. The jet is not like steam leaving a kettle and filling the kitchen. It is more like a tightly guided stream, shaped by fields and motion as it moves outward. Close to the black hole, the jet may begin as a compact, highly energetic flow. Farther out, it can develop structure. It may contain knots, shocks, turbulent patches, and regions where particles are accelerated again. It may interact with gas in the host galaxy. It may push into surrounding material, inflate bubbles, or carve channels through plasma around the galaxy. The jet is not a perfectly smooth laser pointer. It is a physical flow, and physical flows develop complications. Even a river on Earth forms eddies, rapids, and shifting currents. A jet from a supermassive black hole is much faster and thinner, but it too can have internal structure. Those internal structures matter because they help produce the light we see. Particles in the jet, especially electrons, can be accelerated to very high energies. When fast electrons spiral around magnetic field lines, they emit radiation through a process called synchrotron emission. This can produce radio waves, infrared, visible light, and sometimes X-rays, depending on the particle energies and magnetic field strength. Another process can boost lower energy photons to much higher energies when they collide with fast-moving electrons. This is called inverse Compton scattering. Through these and related processes, the jet can shine across a wide range of the electromagnetic spectrum. That is one reason blazars are so different from ordinary stars. A star shines mainly because of hot gas and nuclear fusion in its core. A blazar jet shines because particles are being accelerated in magnetic fields and moving at relativistic speeds. Its light is not simply a warm glow. It is the signature of extreme motion. The jet carries energy outward from the black hole system, and as particles inside it move, collide, spiral, and scatter light, the beam becomes visible to our instruments. It is a black hole system speaking in radio waves, X-rays, gamma rays, and everything in between. The speed of the jet also changes how it appears. Because the material is moving close to the speed of light, relativity becomes impossible to ignore. If the jet points nearly toward us, as it does in a blazar, its radiation is boosted in our direction. This is why the same kind of central engine can look much brighter from one angle than from another. The jet is not only producing light, its motion is concentrating that light toward us. The effect is called relativistic beaming, and it is one of the main reasons blazars can appear so bright across enormous distances. There is a related effect that can make parts of jets appear to move faster than light across the sky. This is called apparent superluminal motion. It sounds as if something has broken the speed limit of the universe, but it has not. The illusion happens because the jet is moving nearly at light speed and nearly toward us. Light emitted from one point in the jet and light emitted slightly later from a closer point arrive closer together in time than we might expect. From our viewpoint, the motion across the sky can appear faster than light, even though the particles themselves remain below light speed. The universe is not cheating. It is using geometry in a way that makes our intuition briefly stumble. A blazar is the extreme version of this viewing effect. We are looking almost straight down one of the jets. That makes the far jet, the one pointing away from us, much harder to notice, while the approaching jet dominates the observation. The object may seem one-sided, not because there is truly only one jet, but because the jet moving toward us is strongly boosted, and the other is dimmed or hidden by distance, angle, and relativistic effects. It is like hearing the approaching part of a siren much more strongly than the receding part, except with light and plasma rather than sound and traffic. The word darkness in this part of the story is therefore slightly misleading, but useful. The black hole is dark inside the event horizon. The space around it is not dark at all. The accretion disk can blaze, the jet can flare. The surrounding galaxy can be affected by energy pouring out from the centre. What looks like darkness from one narrow definition becomes the source of some of the brightest events we can observe. A black hole does not shine from within, but it can create conditions around itself where light is produced with astonishing efficiency. This also helps explain why jets are so important in the life of galaxies. They do not simply leave the centre and vanish politely into space. As they travel outward, they can deposit energy into their surroundings. They can heat gas, push it aside, and create large cavities in the hot material around galaxies and galaxy clusters. This process can change whether gas cools and forms new stars. In massive galaxies and clusters, jets from active black holes may help prevent gas from cooling too quickly, acting like a kind of cosmic thermostat. Not a gentle thermostat, perhaps, more like one installed by someone who believes subtlety is overrated. But the basic idea is that black hole activity can help regulate the environment around it. For a blazar, though, our view is special because we are looking along the jet. That can make it harder to see the jet's full side structure, but it makes the central beam incredibly bright. We are receiving the boosted radiation from material racing almost toward us. The jet becomes a kind of tunnel of information. It tells us about the physics near the black hole, the structure of magnetic fields, the behavior of plasma at high energies, and the power of relativistic motion. The jet is not merely an object to admire. It is a diagnostic tool, a way to study conditions that would otherwise be hidden by distance and scale. Astronomers study these jets using many kinds of telescopes, because no single kind of light tells the whole story. Radio telescopes can trace lower energy emission and reveal structure in the jet. Optical telescopes can follow visible changes and sometimes measure polarization, which gives clues about magnetic field alignment. X-ray telescopes observe very energetic regions and processes. Gamma-ray telescopes detect the highest energy light from the most extreme particle interactions. When a blazar flares, astronomers often try to gather observations across several wavelengths at once, because the timing between different kinds of light can reveal where and how the flare began. Sometimes the flare seems to start close to the black hole. Other times, evidence suggests the particles may brighten farther downstream, after travelling some distance along the jet. This is an important point. A jet does not necessarily shine most strongly at the exact moment it leaves the central region. Particles can be accelerated or re-accelerated farther out. Shocks moving through the jet can energize particles. Magnetic fields can rearrange and release energy. Regions of faster flow can catch up with slower flow. The jet is not born once and then simply coasts unchanged. It remains active, complicated, and capable of producing new light along the way. That makes the jet feel less like a single beam and more like a fast-moving weather system. There are fronts, changes, collisions, and bursts of energy. Of course, it is not weather in the earthly sense. There are no clouds, rain, or umbrellas, and no one is complaining that the forecast was wrong. But the comparison helps because it reminds us that the jet has internal behaviour. It evolves, it has structure, it is shaped both by what happens at the base near the black hole and by what happens as it moves through the galaxy and beyond. The base of the jet remains one of the hardest places to understand because it is small, distant and extreme. Even with advanced telescopes, the region near a supermassive black hole in a distant blazar is difficult to resolve directly. Astronomers often rely on indirect clues: how quickly the brightness changes, how the spectrum shifts, how polarized the light is, how radio structures move, and how flares appear at different wavelengths. Each clue narrows the possibilities. Rapid variability suggests compact regions. Polarization suggests ordered magnetic fields. Apparent fast motion suggests relativistic speeds and small viewing angles. None of these clues alone gives the full answer, but together they create a coherent picture. In that picture, the jet begins because the black hole system is not merely swallowing matter. It is organizing some of the energy of that matter into an outward flow. Gravity pulls the gas inward, but magnetism and rotation give some energy a path outward. The event horizon still does its job. Anything crossing it is lost to the outside universe. But just outside it, before matter falls too far, there is room for energy to be redirected. The jet is born in that narrow region of opportunity, where matter has not yet disappeared and physics is intense enough to launch part of the system away. It is also important to remember that the jet is not made of ordinary gas drifting gently outward. It is plasma, filled with charged particles and electromagnetic fields. In many models, the jet may contain electrons and their antimatter partners, positrons and possibly protons as well. The exact composition can vary or remain uncertain, and it matters because different particles carry energy differently and produce different radiation signatures. If protons are accelerated to very high energies, blazars may also be connected to cosmic rays and neutrinos, which opens another way of studying them beyond light alone. That is where the story begins to touch multi-messenger astronomy, where light is joined by other cosmic messengers. For now, the essential idea stays grounded. A blazar jet escapes the darkness only because it never begins inside the darkness in the first place. It forms in the bright, dangerous region outside the event horizon. It is shaped by an accretion disk, powered by gravitational energy and perhaps black hole spin, guided by magnetic fields and accelerated to relativistic speeds. Its particles produce radiation across the electromagnetic spectrum. If the jet points nearly toward us, relativity boosts its light and turns the source into a blazar. There is something quietly satisfying about this. The old picture of black holes as simple cosmic drains is not wrong, but it is incomplete. They do trap what crosses the horizon. They do mark a boundary beyond which the outside universe receives no direct return. But when black holes are surrounded by matter, they can become part of engines that are anything but simple. The darkness at the centre does not prevent brightness nearby. In fact, the extreme gravity of that darkness helps create the conditions for brightness. The black hole is not a lamp, but it helps power the lamp's machinery. Light from a blazar does not arrive in just one form. It does not politely choose visible light, the small slice our eyes can notice, and leave the rest of the spectrum alone. A blazar is far too energetic for that. It sends out radio waves that can be caught by huge dishes on Earth. It gives off infrared light, visible light, ultraviolet light, X-rays and gamma rays, the most energetic kind of light we regularly discuss in astronomy. In a way, a blazar is not playing one note. It is playing nearly the whole keyboard, from the lowest, longest waves to the sharpest high-energy signals. And our job from this quiet distance is to listen carefully enough to understand what kind of engine could make such a wide sound. The reason begins inside the jet, not inside the black hole, as we've already taken care to say, but inside the jet that forms outside the event horizon and races away from the central region. That jet is not made of ordinary air or gentle gas. It is plasma, a moving stream of charged particles and magnetic fields. The particles can include electrons, possibly positrons, and in some models heavier particles like protons. They move at enormous speeds. They spiral, scatter, collide, and interact with light and fields around them. When charged particles behave that way, they do not stay quiet. They radiate. This is the first thing to remember. Blazars shine across the whole spectrum because the jet contains particles with a wide range of energies moving through a complicated magnetic and radiation environment. Lower energy particles may produce radio waves. More energetic particles can produce visible light or X-rays. Other interactions can push photons up into the gamma ray range. The blazar is not one lamp with one colour. It is a whole set of physical processes happening together, layered on top of one another, and all boosted by the fact that the jet is pointed nearly toward us. A good place to start is with radio waves, because radio astronomy has been crucial to understanding jets from active galaxies. Radio waves have long wavelengths and low energies compared with visible light. They are not low in importance, though. Radio telescopes can reveal structures that ordinary optical telescopes miss. In many active galaxies, radio observations show jets stretching outward from the central region, sometimes ending in large lobes where the jet deposits energy into surrounding space. In blazars, because we are looking almost down the jet, the structure can appear compact and intense near the core, but radio observations can still show details of the jet's motion and shape. The radio light from a blazar often comes from synchrotron emission. That phrase may sound technical, but the idea can be handled gently. When charged particles, especially electrons, move through magnetic fields, they do not travel in perfectly straight lines. They spiral around magnetic field lines. As they curve, they emit radiation. The faster the electrons move and the stronger the magnetic field, the more energetic the radiation can become. Synchrotron emission can produce radio waves, but if the particles are energetic enough, it can also reach infrared, visible, ultraviolet, or even X-ray light. So the same basic process can cover a large part of the spectrum. That is one reason blazar light can seem so broad and restless. The jet contains electrons at many energies. Some are lower energy electrons giving off radio waves. Others are highly energetic electrons giving off shorter wavelength radiation. The spectrum becomes a record of how the particles are distributed, how strong the magnetic fields are, and how the jet is structured. A blazar's light is not just light. It is a report from a population of particles moving through invisible fields at extreme speeds. If you've ever seen dust floating in a shaft of sunlight, you have watched small particles reveal something about the light passing through a room. In a blazar, the comparison is wildly too small, but it gives us a handle. The particles in the jet reveal the magnetic fields and energies around them by the radiation they produce. We cannot see the magnetic fields directly. We cannot scoop up the plasma and place it in a jar. But as the particles spiral and radiate, they leave patterns in the light. Astronomers read those patterns the way someone might read ripples on water to infer the wind. Visible light from a blazar can vary quickly. Sometimes it brightens, sometimes it dims, and sometimes it changes in ways that suggest the jet's inner conditions have shifted. Optical telescopes, including smaller observatories on Earth, can help monitor these changes. That is one of the interesting things about blazars. They're extremely distant and physically extreme, yet some of their visible changes can be followed by many observatories including ones that are not giant space missions. A point of light in a telescope image can become part of a global monitoring effort, because every change in brightness is a clue. Infrared light also matters. Some infrared emission can come from dust around the active nucleus, warmed by radiation from the accretion disk. Some may be connected to the jet itself. In active galaxies, dusty structures can absorb higher energy light and re-emit it at longer wavelengths. In a blazar, because the jet is so dominant from our angle, separating the jet's infrared emission from other sources can be challenging, but that challenge is useful. The different parts of the spectrum help astronomers untangle the ingredients of the central engine: disk, dust, jet, and surrounding galaxy. Moving higher in energy, ultraviolet and X-ray light bring us closer to the more intense activity. The accretion disk around a feeding supermassive black hole can be hot enough to shine strongly in ultraviolet light. X-rays may come from the innermost regions of the accretion flow, from hot plasma near the disk, or from very energetic parts of the jet. In some blazars, synchrotron emission from extremely energetic electrons can reach the X-ray range. In others, X-rays are produced through different interactions involving electrons and photons. The details vary, and that variation is one reason blazars are studied so carefully. Then come gamma rays. Gamma rays are the highest energy form of light, and blazars are among the most important gamma ray sources outside the Milky Way. This is where the jet shows its most extreme side. To make gamma rays, particles need enormous energies, or very efficient ways of transferring energy to light. One common process discussed in blazar science is inverse Compton scattering. The name is a bit unfriendly at first, but the idea is manageable. A low-energy photon, perhaps from the accretion disk, from dust, from starlight, or from the jet's own synchrotron emission, collides with a very fast electron. The electron gives some of its energy to the photon. The photon leaves with much higher energy than it had before. If the boost is strong enough, it can become an X-ray or a gamma ray. You might picture it like a slow tennis ball meeting a very fast racket. The ball comes in gently, the racket hits it, and the ball flies away much faster. In the jet, the photon is the ball, and the electron is the racket, although the racket is moving close to light speed, and the court is a relativistic plasma stream launched from the neighbourhood of a black hole, which would make for a rather difficult afternoon match. Still, the basic exchange is simple. A fast particle can give energy to light. That helps explain how blazars produce some of the most energetic photons we observe. There are different versions of this process depending on where the seed photons come from. If the photons are produced within the jet by synchrotron emission, and then scattered by the same population of electrons, astronomers call it synchrotron self-Compton emission. If the photons come from outside the jet, perhaps from the accretion disk, broadline region, or dusty material around the active nucleus, the process is called external Compton emission. These details matter because they tell us about the environment around the jet. A blazar does not only shine, it lets us infer what kinds of light fields surround the central black hole. Some models also include hadronic processes involving protons and other heavier particles. If protons in the jet are accelerated to extremely high energies, they may produce gamma rays through interactions that differ from the electron-based processes. They may also be connected to neutrinos, ghostly particles that can travel across the universe almost without interacting. This is an active area of research, and scientists are still working out how much of a blazar's highest energy emission comes from electrons, protons, or a mixture of processes. The important point for our journey is that blazar jets are not simple. They may accelerate several kinds of particles, and each kind can leave different fingerprints in the spectrum. The broad shape of a blazar's energy output is often shown as a spectral energy distribution, or SED. This is basically a graph of how much energy the blazar emits at different wavelengths or frequencies. Many blazars show two broad humps in this kind of graph. The lower energy hump is usually associated with synchrotron emission. The higher energy hump is often associated with inverse Compton scattering, or, in some models, hadronic processes. The exact position and strength of these humps vary between blazars. Some peak at lower energies, others peak at X-rays and very high-energy gamma rays. By studying the shape of the graph, astronomers learn about the jet's particles, magnetic fields, and radiation environment. Now that may sound like a lot of graph reading for something that began as a glowing point in the sky, but this is one of the beautiful practical skills of astronomy. A telescope may not give us a close-up photograph of the inner jet. It may not show particles spiraling one by one, but it gives us light sorted by energy, time, and sometimes polarization. From that, scientists build a model. They ask what kind of electron population would make this radio emission. What magnetic field strength would produce this synchrotron peak? What seed photons would explain the gamma rays? Whether the timing of a flare matches one region or another. The spectrum becomes a map, not of shape, but of process. Polarization adds another helpful clue. Light can have an orientation in the way its electric field vibrates. Synchrotron radiation is often polarized because it is produced by charged particles moving in magnetic fields. By measuring polarization, astronomers can learn about how ordered or tangled the magnetic fields are in the jet. If the polarization changes during a flare, it may mean that a shock passed through the jet or that the magnetic field structure shifted. Once again, the blazar does not send us a neat label saying, "Hello, my magnetic field just rearranged itself." It sends changing light, and astronomers interpret the message. The fact that blazars shine across the spectrum also explains why they require teamwork. No single telescope can observe everything from radio waves to gamma rays. Radio telescopes on the ground do one part, optical observatories do another. Infrared telescopes, ultraviolet instruments, X-ray satellites, and gamma-ray observatories each cover different windows. Some wavelengths reach the ground. Others are blocked by Earth's atmosphere and need space-based telescopes. The atmosphere is very useful for keeping life alive, which we should not overlook, but it is not always convenient for gamma-ray astronomy. So we build instruments above it, or use special ground-based methods to detect the showers of particles created when very high-energy gamma rays strike the upper atmosphere. When a blazar flares, this multi-wavelength teamwork becomes especially important. A gamma-ray flare may happen at the same time as an optical flare, or it may lead or lag behind changes at other wavelengths. Radio brightening may appear later, as disturbances move farther down the jet and become visible in radio-emitting regions. By comparing these timings, astronomers can trace where the flare happened and how the disturbance travelled. It is a bit like hearing a sound in one room, then seeing a light flicker in another, then feeling a vibration through the floor. The delays tell you something about the building. The variability is not just decoration. It helps constrain size. If a blazar doubles in brightness over a short time, the emitting region must be small enough for that change to occur coherently. Since information cannot travel faster than light, a rapid flare suggests a compact region. This can be surprising because the whole jet may be enormous, yet the flare may arise from a region much smaller than the larger structure. A blazar can therefore be both huge and tiny in the same observation. Huge in total scale, tiny in the active region responsible for a sudden burst. Different types of blazars also show different spectral behaviour. BL-lac objects tend to have weak or absent emission lines in their optical spectra, while flat-spectrum radio quasars often show stronger emission lines and more evidence of surrounding radiation fields. These differences affect how the jet produces high-energy light. If there are many external photons near the jet, external Compton scattering may be important. If there are fewer external photons, synchrotron self-Compton processes may dominate. The classification is not just a naming exercise. It reflects real differences in the environment around the central engine. Even so, the line between categories is not always as clean as a textbook might wish. Blazars are variable. Their spectra change. Their emission lines can appear weaker or stronger depending on the state of the source and the brightness of the jet. The jet can overwhelm other features, making the underlying galaxy or disk harder to observe. That is another reason the full spectrum matters. If one part of the data is confusing, another part may clarify it. Radio behavior, optical spectra, X-ray slopes, gamma-ray variability and polarization together build a more reliable picture than any single measurement alone. The spectrum also helps us understand distance and the universe between us and the blazar. High-energy gamma rays travelling across cosmic space can interact with background light produced by stars and galaxies over the history of the universe. Some gamma rays are absorbed through pair production, where a gamma ray meets a lower energy photon and the energy turns into an electron and a positron. By studying which gamma rays survive the journey, astronomers can learn about the faint background glow of the universe. In that way, a blazar becomes not only a source of light, but also a probe of all the light it passed through on the way here. This is a quiet but powerful idea. A blazar shines from its own jet, yet its light also carries the imprint of the space between galaxies. The beam starts near a supermassive black hole, crosses the host galaxy, leaves into intergalactic space, passes through the accumulated radiation fields of cosmic history, and finally reaches our instruments. The spectrum we measure is therefore shaped by both the source and the journey. The blazar tells us about itself and about the universe that filtered its light. Across all these wavelengths, one common theme remains. Energy is being moved around. Gravity gives energy to matter falling inward. Magnetic fields and rotation help organize some of that energy into a jet. Electrons and perhaps protons gain energy within the jet. Particles radiate directly or transfer energy to photons. Relativity boosts the emission toward us. The journey through space may absorb or alter some of the highest energy light. By the time the signal arrives, it has become a layered record of physics from the black hole's neighborhood to the cosmic background. That is why saying a blazar is bright is not enough. Bright in what kind of light? Bright when? Bright because of which process? A blazar can be bright in radio waves because of synchrotron emission from electrons spiraling in magnetic fields. It can be bright in visible light because the jet is active and boosted. It can be bright in X-rays because of highly energetic electrons or scattering processes. It can be bright in gamma rays because particles in the jet are giving photons enormous boosts. Each part of the spectrum answers a slightly different question. And for the listener here on Earth, there is something strangely comforting in that. Our eyes see so little. A narrow band of colour useful for sunsets, faces, books, and the mysterious decision to stub one's toe in the dark. But the universe is not limited to what our eyes can receive. It has radio voices, infrared warmth, ultraviolet sharpness, X-ray intensity, and gamma-ray extremes. Blazars remind us that reality is wider than sight. They shine across the whole spectrum because the physics inside them is wide, energetic, and layered. From a practical point of view, this is why blazars are observed again and again. A single observation gives a snapshot. Repeated observations show behavior. Multi-wavelength observations show relationships between different emission processes. A blazar may look calm in radio while flaring in gamma rays, or brighten in optical light while its X-rays shift in a different pattern. Each mismatch is useful. Each agreement is useful. The whole point is to follow the source over time and across light, because the jet changes and the spectrum changes with it. When we ask why blazars shine across the whole spectrum, the answer is not one sentence, but a chain. A feeding supermassive black hole creates a hot accretion environment. Magnetic fields and rotation help launch a relativistic jet. Inside that jet, charged particles are accelerated to many energies. Those particles spiral through magnetic fields, producing synchrotron radiation. They scatter photons to higher energies through inverse Compton processes. Possibly, heavier particles contribute to the most energetic emission. Relativistic motion boosts the light toward us. Different telescopes catch different pieces of the result. The blazar becomes a full spectrum signal from one of the universe's most extreme engines. A blazar rarely behaves like a steady lamp. It is brighter on some days, quieter on others, and during certain outbursts it can rise so sharply that astronomers around the world begin turning telescopes toward the same tiny patch of sky. From here, across distances that may be measured in billions of light years, the object can seem to flicker. Not flicker in the cozy way a candle flickers beside a sleepy window, but in the scientific sense. Its brightness changes with time, sometimes slowly, sometimes quickly, and sometimes so quickly that the change itself becomes one of the most important clues we have. This is where blazars become especially useful. Their light is not just bright, it is variable. A steady object can tell us what it is like at one moment, but a changing object tells us how it works. When a blazar flares, it is as if the jet briefly reveals a moving part inside itself. Something in the flow has shifted, particles have been accelerated, a magnetic field has rearranged, a shock has moved through this plasma, a compact region has brightened. The blazar does not explain itself in words, because galaxies are famously poor at leaving helpful notes, but it does leave a light curve, and that can be read. A light curve is simply a record of brightness over time. On the horizontal axis there is time. On the vertical axis there is brightness, or flux, meaning how much radiation reaches us from the source. A calm star might produce a fairly steady line depending on the star. A pulsating star might rise and fall in a repeating pattern. A blazar, by contrast, often produces a restless line full of changes, flares, drops, plateaus, and sudden shifts. Sometimes it looks like a mountain range drawn by someone who could not decide whether they were sketching weather or listening to jazz. Astronomers watch these light curves at many wavelengths. A blazar may brighten in optical light, then later in radio. It may flare in gamma rays while X-rays change in a different way. It may show a strong outburst in one band and only a mild response in another. These timing differences are not annoyances, they are information. If a gamma-ray flare happens before a radio flare, that may suggest the most energetic emission came from a compact region closer to the base of the jet, while the radio emission became visible later as the disturbance moved outward and the region became more transparent at longer wavelengths. The order of events becomes a map of motion. This is one reason time matters so much in blazar science. We cannot watch a single particle travel down the jet. We cannot float beside the beam with a clipboard and a very brave pair of sunglasses. Instead, we watch how the light changes. A flare begins, it rises, it peaks, it fades, sometimes it repeats, sometimes it appears in several wavelengths at once, sometimes it arrives with a change in polarization, telling us that the magnetic field structure has shifted. Each change is a clue about where the emission happened, how large the emitting region may be, and what physical process released the energy. There is a simple rule behind much of this reasoning, and it comes from the speed of light. No signal can travel faster than light. That means an object cannot change as a whole faster than light can cross it. If a region brightens dramatically over one day, then the region responsible for that coordinated brightening cannot be much larger than one light day across, once the effects of relativistic motion are accounted for. If it changes over an hour, the region must be smaller. If it changes over minutes, then the emitting zone is shockingly compact by galactic standards. This is one of the most powerful tools astronomers have. The blazar may be so distant that it appears as a point, but its flickering gives away the scale of its internal parts. A point of light on the sky can contain a region smaller than a solar system, embedded inside a jet that stretches across thousands of light years, inside a galaxy that may span tens or hundreds of thousands of light years. Time becomes a kind of ruler, not a wooden ruler, and not one you should try to keep in a desk drawer, but a physical limit set by causality. Fast change means small source. There is a complication, of course, because blazars enjoy giving us complications. The jet is moving almost toward us at nearly the speed of light, Because of that, the timescales we observe are affected by relativistic motion. The approaching jet's light is boosted and the timing of events can be compressed. To us, a process inside the jet may appear to happen faster than it would in the jet's own frame of reference. Astronomers account for this with something called the Doppler factor, which describes how motion toward us changes the observed brightness, frequency, and timing. Without that correction, we would misjudge the size and energy of the emitting region. There is another timing effect from the expansion of the universe. For very distant blazars, cosmic expansion stretches the light as it travels. Wavelengths are redshifted, and time intervals are stretched too. A flare that lasted a certain amount of time in the blazar's own frame may appear longer to us because the universe expanded while the light was on its way. So the observed timing is shaped by two opposite influences. Relativistic motion in the jet can compress the timescale, while cosmological redshift can stretch it. The light curve we receive has been shaped by both the source and the journey. That may sound like an inconvenience, but it is also a gift. Because these effects are predictable, they allow astronomers to extract more information. The observed flickering tells us not just that something changed, but how fast the jet is moving, how compact the emission zone might be, and how far away the source is. The timing is layered. There is the time inside the jet, the time affected by the jet's motion, the time stretched by cosmic expansion, and the time recorded by our instruments. A blazar flare is not simply an event, it is an event translated through relativity and distance. In some cases, blazars have shown variability on very short timescales. High-energy emission can change in hours, and in certain extreme observations, even shorter times have been reported. This is difficult to explain with a very large emitting region. If gamma rays are changing rapidly, the region producing them must be compact, or the emission must come from smaller structures inside a larger flow. That has led to ideas such as turbulent cells within the jet, magnetic reconnection events, tiny fast-moving regions sometimes called mini-jets, or shocks that briefly energize particles in a localized zone. The jet may look like one beam from far away, but inside it, there may be many smaller zones turning on and off. Magnetic reconnection is one idea that appears often in discussions of rapid variability. In plasma, magnetic fields can become twisted and stressed. When field lines rearrange, magnetic energy can be released quickly and converted into particle energy. Something similar happens in solar flares, though the scale and environment are very different. In a Blazar jet, reconnection could accelerate particles rapidly and produce sudden bursts of radiation. It is a way for stored magnetic energy to become light. The process may help explain why some flares rise so quickly, and why the jet can produce high-energy photons from very compact regions. Shocks are another important possibility. A shock is a sudden change in flow conditions, like a compression wave moving through the plasma. If faster material in the jet catches up with slower material, or if the jet interacts with a standing feature, particles can be accelerated at the shock front. Those particles then radiate. A shock moving down the jet could produce a flare that appears first at higher energies and later at lower energies, depending on how the region evolves and becomes transparent. This gives astronomers a way to connect timing patterns with physical models. The difficulty is that more than one process can produce similar-looking changes. A flare might be caused by a shock, magnetic reconnection, turbulence, a change in the supply of particles from the central engine, or some combination of these. Real jets do not need to choose one explanation just to make our diagrams tidier. They may use several. That is why astronomers do not rely on brightness alone. They look at the flare shape, the spectrum, the timing between wavelengths, the polarization, and the behavior before and after the outburst. A single flare can be examined like a small weather system inside the jet. The shape of a flare matters. Some flares rise quickly and fade slowly, others rise and fall more symmetrically. A fast rise can suggest a sudden injection of energetic particles, while a slower decay may reflect cooling, expansion, or the time it takes particles to lose energy. If the flare fades faster at high energies than at low energies, that may reveal how quickly the most energetic particles cool. If several flares overlap, the light curve may look messy, not because the data are poor, but because the source is doing several things at once. The blazar is not obligated to perform one clean experiment at a time. Cooling is another piece of the timing story. Particles in the jet lose energy as they radiate. Electrons emitting synchrotron radiation in strong magnetic fields can cool quickly. Electrons scattering photons to gamma ray energies can also lose energy through radiation. The higher the energy, the shorter the cooling time may be, depending on conditions. This means high energy light can change faster than lower energy light. X-rays and gamma rays may trace the freshest, most energetic particles, while radio waves may trace regions farther downstream or longer-lived populations of particles. The spectrum changes because the particles themselves are evolving. Radio variability often works on longer timescales than gamma ray variability. One reason is that radio emission may come from larger regions farther out in the jet. Another is that parts of the jet can be opaque to radio waves at first, meaning the radio signal cannot escape immediately from the densest inner regions. As the disturbance moves outward and expands, it may become visible at radio frequencies later. This delay can help astronomers estimate how disturbances travel down the jet. It is a bit like seeing lightning first and hearing thunder later, except the timing is not caused by sound moving slowly through air. It is caused by emission regions, opacity, and a jet moving at relativistic speed. Optical variability can be especially rich because it is easier to monitor regularly. Many blazars are watched night after night by telescopes that measure their visible brightness and polarization. Sometimes optical polarization rotates during a flare, suggesting that the emitting region is moving through a changing magnetic field structure, or that the field itself is reorganizing. A change in polarization can be just as revealing as a change in brightness. It tells us about the direction and order of the magnetic fields, not only about how much light is being produced. Imagine trying to understand a distant dancer by watching only their shadow on a wall. Brightness tells you how large or dark the shadow is. Color tells you what kind of light is involved. Timing tells you how quickly the dancer moves. Polarization, in this loose comparison, tells you something about the orientation of the room's hidden mirrors. It is not a perfect comparison, but it captures the point. We are not seeing the jet directly in full detail. We are inferring motion, structure, and fields from the signals that reach us. Sometimes blazars show hints of repeating or quasi-periodic behavior, where flares seem to recur on certain timescales. These claims are treated carefully, because random variability can sometimes imitate patterns. Blazar-like curves often contain red noise, meaning slower variations can have more power than faster ones, and patterns may appear by chance in uneven data. Astronomers use statistical tests to decide whether a possible rhythm is real or just the jet's ordinary restlessness wearing a temporary disguise. In some cases, repeated behavior may suggest a binary black hole system, jet precession, orbiting structures in the disk, or recurring changes in the flow. But caution is important. The universe has no shortage of ways to look suspiciously patterned without actually keeping a schedule. This connects to the phrase in our title idea, time flickers. The blazar is not literally turning time on and off. Time at the distant galaxy continues in its own frame, shaped by gravity and motion as physics requires. What flickers is the light we receive, and through that light, our view of processes unfolding near a supermassive black hole. But the changes are so tightly connected to size, motion, and energy that time becomes part of the measurement. The brightness does not just tell us how powerful the source is, the timing tells us how compact and fast the source must be. There is also a human side to watching a blazar change. Some astronomical objects require patience across generations, A galaxy merger may take hundreds of millions of years. A star's lifetime may span billions. But a blazar flare can happen while astronomers are awake, or while they're trying to sleep, which is often when the universe chooses to become dramatic. Alerts may go out when a gamma-ray telescope detects increased activity. Observatories may respond quickly. Data from different instruments may be gathered and compared. For a little while, a distant galaxy becomes a current event. That is an odd thought. A flare we call current may have happened billions of years ago in the blazar's own history. The light reaches us now, so it becomes news now. In astronomy, now depends on the messenger. When we say a blazar is flaring tonight, we mean the light arriving tonight is brighter. The event itself occurred when the light was emitted, long ago for distant sources. The telescope's present is not the source's present. This is not a problem. It is simply how observation works in a universe where light travels at a finite speed. So a blazar's flickering is always both immediate and ancient. The detector records a change tonight. A scientist plots a new point on a light curve. A telescope sees the source brighten. Yet the photons began their journey before our civilization existed, perhaps before Earth's surface looked much like it does now, perhaps when the universe itself was in a much younger stage. The flare is a signal from the past arriving in our present. That makes blazar variability feel almost like a conversation across time, though it is not a conversation in any intentional sense. The blazar emitted light. The universe carried it. We were here when it arrived. Because blazars are so variable, long-term monitoring is essential. A single bright flare might be exciting, but years of observations show patterns of behaviour. Some blazars spend most of their time in a lower state, with occasional bursts. Others remain active for long stretches. Some have dramatic high states that dominate their energy output. Long light curves help astronomers separate unusual events from typical behaviour. They also reveal whether the source changes its spectrum when it brightens. Does it become harder, meaning more high-energy emission? Does the synchrotron peak shift? Do gamma rays rise more strongly than optical light? Each trend helps identify what is happening inside the jet. In a quiet way, this is similar to learning someone's habits. If you only saw a neighbour once sprinting down the street with a suitcase and a sandwich, you might draw the wrong conclusions. If you watched over many months, you would learn whether that was unusual or simply how they handle Mondays. Blazars also need context. A flare is more meaningful when we know what the source usually does. The long record makes the sudden change understandable. Variability also helps astronomers estimate the power of relativistic beaming. Because the jet is aimed toward us, even small changes inside it can appear amplified. Brightness increases can be dramatic, and timescales can appear shortened. If a source changes too quickly and shines too intensely, it would create a problem if there were no relativistic motion. High-energy gamma rays inside a dense, compact region should collide with lower-energy photons and be absorbed. For gamma rays to escape, the region often needs to be moving relativistically, which reduces the photon density in the source frame and changes the conditions. In that way, the very fact that we see rapid gamma-ray flares tells us the jet must be moving extremely fast. This is a wonderful example of indirect reasoning. Astronomers do not need to stand beside the jet with a speed camera. They can infer the speed because the light escaped. If the emitting region were too compact and not moving fast enough, the gamma rays would not make it out. Since they do, the jet's motion must help solve the transparency problem. The flickering tells us about size. The gamma ray survival tells us about speed. The brightness tells us about energy. Together they form a physical picture. There is still uncertainty, of course. The exact location of gamma ray emission in blazar jets remains an active question. Some evidence suggests it can arise close to the central black hole, near the broadline region in certain objects. Other observations suggest emission farther downstream, perhaps several parsecs from the black hole. Different blazars may behave differently, and even the same blazar may produce flares from different regions at different times. The jet is long, structured, and changing. There may not be one universal answer, which is inconvenient for neat summaries but very normal for nature. The phrase distant galaxy also deserves attention. A blazar is not just a small object flickering in isolation. It is the center of a galaxy, and the flicker comes from a region embedded in a much larger system. When the jet brightens, the host galaxy does not suddenly brighten as a whole. The flare comes from the active nucleus and jet. The stars of the galaxy continue their long, quiet orbits. From our viewpoint, however, the central light can overwhelm everything else. A small region near the black hole can dominate the signal from billions of stars. That is why blazar variability can be so dramatic. It is not the galaxy's entire body changing, it is the restless central engine briefly taking over the view. A flare can also trigger follow-up searches for other messengers. In some cases, scientists look for neutrinos that may be associated with blazar activity. Neutrinos are extremely difficult to detect because they rarely interact with matter, but that also means they can travel from dense cosmic environments that light may not escape from easily. If a blazar flare coincides with a high-energy neutrino, it raises the possibility that the jet is accelerating protons or other hadrons, not just electrons. This is a developing field, and not every association is certain, but it shows how blazar variability can connect electromagnetic astronomy with particle astronomy. For our slow journey, the essential point is that blazars change because their jets are active, compact, and moving at relativistic speeds. The flicker is not random decoration. It is a direct clue to physical conditions. The rise time of a flare limits the size of the emitting region. The timing between wavelengths suggests where radiation is produced. The spectrum during the flare reveals particle energies and cooling. Polarization changes point toward magnetic structure. Gamma-ray transparency requires fast motion. Long-term monitoring shows whether the flare is unusual or part of a broader pattern. And somewhere behind all of this is the black hole system we have been following from the start. Gas falls inward. The disk heats, magnetic fields twist, the jet launches, particles accelerate, light is produced across the spectrum, then the brightness changes, and because it changes, we get to learn. A steady blazar would still be interesting, but a flickering blazar is far more talkative. It lets us measure the engine not only by how bright it is, but by how quickly it can change its mind. As the light curves build night after night, year after year, they turn distant galaxies into time records. Each point on the graph is a small arrival from a remote jet. Each flare is a message from a compact region where particles gained energy long ago. Each quiet interval is also part of the story, showing the baseline from which the next brightening will rise. The blazar's time is not our time exactly, stretched by distance and shaped by relativistic motion, but it reaches us all the same. Beyond the flicker of a single jet, the story begins to stretch outward and backward. A blazar is not only a bright object in space, it is also a marker in time. Because light does not arrive instantly, every distant blazar shows us an earlier version of the universe. The farther away it is, the older its light is, and the younger the universe was when that light began its journey. So when astronomers study blazars billions of light years away, they are not simply looking at strange galaxies in remote places. They are looking at powerful black holes that were already awake when the universe itself was still young. That is one of the reasons blazars matter so much. They are bright enough to be seen across enormous distances, and because their jets are aimed close to our line of sight, their light is boosted toward us. This makes them useful signposts in the early universe, where many objects are too faint to study easily. A normal galaxy from that era may be difficult to detect because its starlight is stretched, dimmed, and spread thin by distance and cosmic expansion. But a blazar has an advantage. Its central engine is extremely powerful, and its jet acts like a beam pointed near Earth. That beam can carry information from a time when galaxies were still building themselves, and supermassive black holes were growing at a pace that still challenges our understanding. To see why this is so important, we need to think about what the early universe was like, not at the very beginning, not in the first few seconds after the Big Bang, but hundreds of millions to a few billion years later. By then, the first stars had formed, the first galaxies were assembling, gas was falling into growing structures shaped by gravity. Black holes were appearing and gaining mass. The universe was no longer smooth and simple. It had begun forming the large cosmic web of galaxies and dark matter that we see today. But it was still young enough that many of its larger structures had not had much time to grow. That creates a puzzle. Some distant active galaxies contain supermassive black holes with masses of hundreds of millions or even billions of suns. When we find such a black hole in the early universe, we have to ask a very practical question. How did it get so big so quickly? A black hole cannot grow without material. It has to feed on gas, merge with other black holes, or begin from a large seed. Even if it feeds efficiently, radiation from the accretion disk can push back on falling gas, limiting the rate of growth. So when astronomers find a very massive black hole at a very early time, it is not just impressive. It is a clue that our models of black hole formation and growth must explain some very fast building. Blazars sharpen that question, because their jets are usually associated with massive active black holes. If we observe a blazar at high redshift, that means a supermassive black hole was already in place, already feeding, and already launching a relativistic jet when the universe was much younger than it is now. The jet also has to be aimed close enough to us for the object to appear as a blazar. That alignment is rare. For every blazar pointed toward us, there may be many similar jetted active galaxies pointed in other directions, less strongly boosted and harder to identify. This means one distant blazar can hint at a larger hidden population of active black holes in the early universe. That is a subtle but powerful idea. A blazar is not only one object, it is a statistical messenger. Because the jet must be aimed close to Earth, finding even a small number of very distant blazars suggests that many more jetted black holes may exist with jets pointed elsewhere. It is like seeing one lighthouse beam sweep across you from a far coastline and realizing there may be many other lighthouses along the shore whose beams are turned away. The one beam you catch tells you something about the wider population. In astronomy, orientation becomes a clue to numbers. This matters for early black hole growth. If distant blazars point to a larger population of massive jetted black holes, then the early universe may have built these objects more efficiently than expected. Perhaps some black holes began from heavier seeds than the remnants of ordinary first stars. Perhaps gas in young galaxies flowed inward at extremely high rates. Perhaps jets and magnetic fields changed how accretion worked. Perhaps some black holes grew through repeated mergers in dense early environments. None of these possibilities is simple, and the answer may involve more than one path. But distant blazars make the problem harder to ignore. A helpful way to imagine the issue is to think of walking into a young forest and finding several enormous old-looking trees. You would naturally ask how they grew so tall in so little time. Did they start as unusually large saplings? Did they grow in unusually rich soil? Did the forest begin earlier than you thought? Did your estimate of the age need correction? Early supermassive black holes raise a similar set of questions. Their existence does not break physics, but it demands a good explanation. Blazars, because they're so bright and visible across distance, help reveal some of the most extreme examples. The redshift of a distant blazar helps astronomers estimate how far back in cosmic history they are looking. As the universe expands, the wavelength of light travelling through it stretches. Light emitted in ultraviolet or visible wavelengths may arrive at Earth shifted into redder or infrared wavelengths. The larger the redshift, the farther back we are looking, generally speaking. A high redshift blazar is therefore a blazar seen when the universe was much younger. Its light has been stretched by expansion during the long journey to us. Measuring that redshift, often through spectral features, gives astronomers a time marker. Spectra are especially important here. A spectrum spreads light into its component wavelengths, like a much more detailed version of a rainbow. In the spectrum of an active galaxy, astronomers may see emission lines from gas near the black hole or absorption features from material along the line of sight. Those features are shifted by cosmic expansion. By measuring how far they have moved from their expected wavelengths, astronomers determine redshift. In a blazar, this can be challenging because the jet's bright, smooth emission may overwhelm some spectral features. The same beam that makes the blazar easy to find can make some measurements harder. The universe has a sense of humour, or at least an impressive commitment to making scientists work. Once the distance and redshift are known, the blazar becomes a probe of early cosmic conditions. Its brightness tells us about the jet and the central engine. Its spectrum tells us about particles, magnetic fields, and radiation processes. Its host galaxy, if it can be studied, may reveal how massive galaxies were forming at that time. Its black hole mass, estimated through several methods, gives clues about growth rates. Its jet shows that large-scale magnetic and accretion processes were already operating in young galaxies. A distant blazar is therefore a compact bundle of information about an early galaxy, its central black hole, and the environment around it. The early universe was also a time when the space between galaxies was changing. In the first few 100 million years, much of the hydrogen gas between galaxies was neutral. Then radiation from the first stars, galaxies, and active black holes gradually rionized that gas, turning it into a more transparent plasma. This period is called the epoch of rionization. Very distant active galaxies, including rare blazars, can help scientists explore that era and the periods around it. Their light travels through the intervening universe carrying traces of what it passed. Absorption patterns and missing light at certain wavelengths can reveal the state of gas along the path. Blazars are not the only tools for studying the early universe, of course. Astronomers also use galaxies observed with infrared telescopes, quasars, gamma-ray bursts, the cosmic microwave background, and many other sources. But blazars have a special role because of their jets. A quasar may be bright because of its accretion disk and surrounding active nucleus. A blazar includes that active central system plus a relativistic jet aimed close to us. That makes it unusually luminous and variable, especially at high energies. It allows astronomers to study not just growing black holes, but growing black holes that have already developed powerful jets. That raises another question. How do such jets form so early? A strong jet may require a rapidly spinning black hole, a magnetized accretion disk, and a particular flow of matter near the center. If a very distant blazar has a powerful jet, then these conditions were already present at an early stage of cosmic history. That suggests young galaxies could create highly organized central engines relatively quickly. Gas had to reach the center. Magnetic fields had to be amplified or arranged. The black hole had to become massive and perhaps spin rapidly. The jet had to break out and remain focused. All of that had to happen within the available time. This is not impossible, but it is impressive. The universe is very good at building structure, given gravity, gas, dark matter, and enough time. The surprise is sometimes how little time seems to be required. Distant blazars show us that some supermassive black holes were already not only large, but actively shaping their surroundings and launching jets when the universe was still in its early growth. These objects are like evidence of advanced machinery found in a young workshop. The workshop itself is still being assembled, and yet in one corner an engine is already running at full power. There is another reason early blazars are valuable. Their jets can emit high-energy radiation that interacts with the background light filling the universe. Gamma rays travelling across cosmic distances may be absorbed by photons from the extragalactic background light. the accumulated glow of stars and galaxies throughout cosmic history. By studying which gamma rays arrive and which seem to be missing, astronomers can learn about that background light. This is difficult work because the source itself is variable and complex, but the principle is important. A distant blazar's light is affected by the universe it crosses. The beam becomes a probe of the cosmic fog. We can think of this a little like shining a flashlight through mist. If the light comes through dimmed or reddened, you learn something about the mist, not only about the flashlight. With blazars, the mist may be background light, gas, magnetic fields, or intervening matter across billions of light years. The universe between the blazar and Earth is not empty in a perfect sense. It contains faint radiation fields, thin gas, large-scale structure, and sometimes intervening galaxies. A blazar beam passes through all of that, and by the time it reaches us, it carries the fingerprints of the journey. Some early blazars may also help scientists estimate how common massive black holes were at certain times. This is where the alignment issue becomes important again. Because only jets pointed close to us appear as blazars, every detected blazar implies a larger parent population of similar sources with jets pointed elsewhere. The exact number depends on the jet's speed and opening angle, but the general idea is straightforward. If one narrow beam happens to point at us, there should be many beams pointing in other directions. So when astronomers find a high redshift blazar, they do not merely add one black hole to the census. They revise expectations for how many massive jetted black holes may have existed then. This can challenge models of early black hole formation. If the implied population is large, then theorists must explain how so many massive black holes grew quickly enough. Did they begin as the remnants of the first massive stars, then feed at or above usual limits? Did some form through direct collapse of large gas clouds, creating heavier seeds from the start? Did dense star clusters produce intermediate mass black holes that merged and grew? Did early galaxies funnel gas more efficiently than later galaxies? These questions remain active, and blazars provide some of the clues that keep them alive. The role of jets in growth is also debated. On one hand, jets carry energy away and might reduce the amount of material that falls into the black hole. On the other hand, the presence of a jet may indicate special conditions, such as strong magnetic fields and high spin, that are linked to rapid growth or efficient accretion. Some studies suggest that jetted black holes in the early universe may be unusually massive compared with other populations. If that is true, it may mean that the path to becoming a powerful jetted source is tied to rapid black hole assembly. The exact cause and effect are still not fully settled. Nature is rarely kind enough to label one arrow cause and another effect for us. What we can say is that distant blazars reveal early maturity. They show us black holes that had already reached enormous masses, galaxies that had already built active centers, and jets that had already become relativistic cosmic structures. This is not the whole early universe, but it is one dramatic part of it. The young cosmos was not only full of forming stars and small galaxies gathering into larger ones, it also contained extreme engines capable of shining across nearly all of cosmic time. That changes how we picture the early universe. It was not simply a quieter, smaller version of the universe today. In some ways, it was more active. Gas was more abundant. Galaxies were interacting and merging more often. Star formation rates were higher in many systems. Black holes had fuel available. Active galactic nuclei were more common at certain periods. Distant blazars fit into this busy picture. They are not random oddities. They are high-energy examples of a broader era of growth. Of course, finding them is difficult. Their rarity, distance, and variability make them challenging targets. Astronomers search for candidates using radio surveys, infrared colours, optical spectra, X-ray detections, and gamma-ray observations. A source may first appear as a radio object. Follow-up observations may reveal a flat radio spectrum, strong variability, or a compact core. Spectroscopy may measure its redshift. High-energy observations may confirm blazar-like behaviour. Each discovery requires careful checking because the label matters. a misidentified source could lead to wrong conclusions about early black hole populations. The most distant candidates are especially valuable and especially demanding. At very high redshift, visible light emitted by the source may have shifted into infrared by the time it reaches Earth. Dust, gas, and intervening absorption can complicate the view. The host galaxy may be extremely faint compared with the jet. The jet itself can hide spectral features needed for distance measurement. So the process of confirming a distant blazar can take many instruments and many observations. It is not a quick glance. It is more like slowly recognizing a face through fog, using every available angle. Once confirmed, though, a distant blazar becomes a rare window. It tells us that a supermassive black hole existed at that time. It tells us that the black hole was active. It tells us that the central region could launch a relativistic jet. It suggests a larger population of similar objects with other orientations. It provides a bright background source whose light may reveal intervening material. It helps connect the growth of black holes with the growth of galaxies. One source, carefully studied, can touch many questions. There is also a scale of patience here that is easy to miss. The blazar's light may have travelled for more than 12 billion years before reaching us. During that time, Earth formed, cooled, developed oceans, produced life, changed atmospheres, grew forests, lost them, grew them again, watched continents drift, saw dinosaurs come and go, and eventually produced astronomers who built detectors sensitive enough to catch the old signal. The blazar did not wait for us, it simply emitted light. But by the time the light arrived, there was a planet ready to understand it. That is not a scientific requirement, but it is a pleasant thought to take with you into the dark. Still, the science stays grounded. Distant blazars reveal that supermassive black holes and relativistic jets existed early. They help constrain how quickly black holes grew. They imply hidden populations of jetted active galaxies. They probe background light and intervening matter. They show that young galaxies could host highly energetic central engines. Their variability and spectra provide measurements of jet physics under conditions from long ago. They are not just bright curiosities, they are evidence. As astronomers gather more data, the picture will become clearer. New radio surveys can find more jet candidates. Infrared telescopes can identify distant active nuclei whose light has been stretched by cosmic expansion. X-ray and gamma-ray observatories can measure the high-energy output. Large optical and infrared spectroscopic campaigns can determine redshifts and black hole masses. Each new distant blazar either fits the current models or gently pushes against them. The pushing is useful. It is how science improves. A model that cannot handle the objects we find must be adjusted, expanded, or replaced. For the listener drifting along with this story, the main idea can be held simply. Blazars reveal the early universe because their jets make active black holes visible across enormous distances. When we find one far away, we are seeing a supermassive black hole that was already feeding and launching a jet when the universe was young. That discovery helps us ask how the first giant black holes formed, how fast they grew, how galaxies fed them, and how their energy affected the space around them. A blazar is a beam from a galaxy, but it is also a time capsule. The names can get a little slippery here, so it is worth slowing down before they start behaving like labels on a drawer that someone organised in the dark. Blazar, quasar, active galaxy, active galactic nucleus, radio galaxy, Seyfert galaxy, BL-lac object, flat spectrum radio quasar. At first, it can sound as if astronomers looked at one bright thing in space, became very excited, and then gave it 6 names before breakfast. And to be fair, astronomy has had moments rather like that. But beneath the terminology there is a clear idea, and once we see it, the whole family of objects becomes much easier to hold in the mind. The broadest term is active galaxy. That means a galaxy whose centre is unusually bright because its central supermassive black hole is actively feeding. The important part is not that the galaxy contains a black hole. Most large galaxies seem to contain supermassive black holes in their centres, including our own Milky Way. The important part is that enough gas and dust have moved close enough to the black hole to form a hot accretion disk and release tremendous energy. When that happens, the centre of the galaxy becomes an active galactic nucleus, often shortened to AGN. It is the bright, energetic core of the galaxy, powered by matter falling toward the central black hole. So an active galaxy is the whole galaxy. The active galactic nucleus is the bright central engine. The galaxy contains stars, gas, dust, dark matter, and a long history of formation. The nucleus is the compact region near the supermassive black hole where the most intense energy is being released. That distinction is simple, but useful. If the galaxy is the whole house, the active nucleus is the furnace roaring in the basement, though in this case the furnace may produce jets longer than the house itself, which would probably violate several building codes. A quasar is one kind of active galactic nucleus, generally an extremely luminous one. The word quasar comes from quasi-stellar radio source, because the first quasars looked like stars through optical telescopes, almost point-like, but they had unusual radio emission and spectra that revealed enormous distances. They were not stars at all, they were the brilliant centres of distant galaxies. Because their host galaxies were so far away, and the central light was so intense, the surrounding starlight could be hard to see. They looked star-like, but their power came from supermassive black holes feeding at the centres of galaxies. That is one of the recurring themes in astronomy. Something looks small because it is far away. Something looks simple because the details are hidden. Something looks like a star because the telescope cannot yet separate the glare from the galaxy around it. Then better observations arrive, and the small, simple star-like point becomes a monster engine in a distant galaxy, which is a fairly dramatic plot twist for a dot of light. Quasars are among the brightest steady objects in the universe. Their accretion disks can release enough radiation to outshine their host galaxies. They can be seen across billions of light years, which is why they are so useful for studying the distant universe. A quasar does not have to be a blazar. That is the part that matters for our story. Many quasars are bright active galactic nuclei with powerful accretion disks, and some have jets. But unless a jet is pointed close to our line of sight and dominates the way we observe it, we do not usually call it a blazar. A blazar is a special case. It is an active galactic nucleus with a relativistic jet aimed almost directly toward us. Often, blazars are described as a subclass of quasars, especially when they show strong quasar-like emission features. But the defining feature is the viewing angle and the jet. The central engine launches jets in opposite directions. One jet points toward us, or nearly toward us. Because the particles in the jet are moving close to the speed of light, relativistic effects boost the light in our direction. This makes the object appear especially bright, highly variable and often strong in gamma rays. So the difference between a quasar and a blazar is not always that the engine is completely different. It may be the same broad kind of engine seen from a different angle, with the jet becoming much more important in our view. Imagine a car with headlights on at night. From the side, you see the car and a bit of glow. From in front, the headlights dominate everything. The car has not changed. Your angle has. A blazar is like looking almost straight into the headlight beam of an active galaxy, except the headlights are relativistic jets from the neighbourhood of a supermassive black hole, which is why one should always be careful when improving metaphors with astrophysics. This idea is part of what astronomers call unification models of active galactic nuclei. The basic thought is that some different-looking active galaxies may actually be similar kinds of object, viewed from different directions, or seen through different amounts of surrounding dust, or observed at different levels of jet strength. The same central ingredients can appear in different ways: a supermassive black hole, an accretion disk, hot gas, clouds producing emission lines, a dusty torus around the central region, and sometimes relativistic jets. Change the viewing angle, and the appearance changes. If we look at an active galaxy from the side, thick dust around the nucleus may block part of the central light. We might see some features clearly and others only indirectly. If the galaxy has large jets pointing sideways across the sky, we may classify it as a radio galaxy. If the central disk is very bright and relatively unobscured, we may call it a quasar. If the jet is pointed almost at us, and its boosted light dominates the signal, we call it a blazar. The object is not wearing a name tag. We assign the name based on what reaches our telescopes. That is why these categories can feel strange at first. They are not always separate species in the way a cat and a pine tree are separate species. They are sometimes more like different views of related machinery. A radio galaxy can be a jetted active galaxy viewed from an angle where the jets spread across the sky. A blazar can be a similar jetted system viewed nearly along the jet. A quasar can be a bright active nucleus whose central emission is visible and intense. A Seyfert galaxy can be a less luminous active galaxy, often closer and easier to see with its host galaxy. These labels overlap through physics, brightness, angle, and history. The word active is doing a lot of work. A normal galaxy can contain many stars and still not have an active nucleus. Its central black hole may be quiet, like a sleeping bear after an unusually sensible dinner. In an active galaxy, the black hole has fuel. Gas is falling inward. The accretion disk heats. Radiation pours out. In some cases, jets form. This activity makes the center much brighter than expected from stars alone. The active nucleus can shine in radio, infrared, visible, ultraviolet, X-rays, and gamma rays, depending on the structure and processes involved. Quasars represent the very luminous end of this active family. Historically, they were first recognized as mysterious star-like radio sources with strange spectra. Once astronomers understood their redshifts, it became clear they were extremely distant and therefore incredibly powerful. They were not small nearby oddities. They were brilliant galaxy centers across cosmic time. Many quasars are seen from the early universe, because they were more common when galaxies had more gas available and black holes were growing rapidly. A quasar tells us that a supermassive black hole was feeding efficiently enough to produce enormous light. Blazars add the jet orientation to that picture. The accretion disk may still be present. The black hole is still central. The host galaxy is still there. But the jet aimed toward us becomes the star of the observation. It can overwhelm the disk's light. It can make emission lines appear weaker by adding a bright, smooth continuum. It can cause rapid variability. It can produce strong polarization. It can shine brightly in gamma rays. Because the jet is boosted, a blazar may look far more extreme than the same object would look from the side. This is not because the object is pretending. It is because relativity and perspective are powerful editors. Inside the blazar family, there are also two common types, BL-lac objects and flat-spectrum radio quasars. BL-lac objects are named after BL Lacertae, an object that was originally mistaken for a variable star. They tend to have weak or absent emission lines in their optical spectra. Their jet emission can dominate so strongly that the usual spectral features from surrounding gas are hard to see. Flat-spectrum radio quasars, often shortened to FSRQs, show stronger emission lines and usually have more obvious evidence of surrounding gas and radiation fields. Both are blazars because their jets are pointed close to us, but their spectra reveal differences in the environment around the central engine. This difference matters because emission lines come from gas near the active nucleus. In many quasars, clouds of gas move rapidly around the black hole and produce broad emission lines when they are illuminated by the accretion disk. Farther out, other gas clouds can produce narrower lines. If those lines are strong, they tell astronomers about the gas and radiation around the black hole. In a BL-lac object, the jet can be so dominant, or the surrounding line-emitting gas so weak that these features are faint or missing. In a flat-spectrum radio quasar, The line-emitting regions are more obvious. So even within blazars, we can learn about the central environment by looking at what the jet does not completely hide. Now, where do radio galaxies fit? A radio galaxy is an active galaxy with strong radio emission, often from large jets and lobes extending far beyond the visible galaxy. If the jet is not pointed at us, we may see the extended structures more clearly. The approaching jet is not boosted straight into our line of sight in the same way, so the object may look less variable and less dominated by the central beam. In the unification picture, some radio galaxies may be the misaligned relatives of blazars. The same kind of jetted engine seen from the side becomes a different class in our catalogue. This is a wonderfully practical reminder that astronomy is not only about what objects are, but also about how they look from here. Earth's location and the object's orientation shape the classification. We're not walking around these galaxies with a flashlight and a clipboard, viewing them from every angle like furniture in a shop. We get one line of sight. From that line of sight, we infer the structure. If the jet points toward us, the object enters the blazar family. If it points away, we may classify it differently. The same cosmic engine can wear different observational clothes. Seyfert galaxies are another part of the active galaxy family. They're usually less luminous than quasars and often found relatively nearby, so their host galaxies can be studied more easily. Seyferts have bright nuclei and emission lines, but their central engines are not usually as overwhelmingly luminous as quasars. They can be divided into types depending on which emission lines we see, often linked to whether our view of the inner region is blocked by surrounding dust. Seyferts remind us that active galactic nuclei come in a wide range of power levels. Not every feeding black hole becomes a quasar, and not every active galaxy launches a blazar-like jet. The dusty torus is another useful piece of the puzzle. Many active galaxy models include a thick donut-shaped region of dust around the central accretion disk and black hole. If we view the system face-on, we may see the bright inner regions more directly. If we view it edge-on, the dust may block our view of the disk and broadline region. The same nucleus can therefore look different depending on orientation. This is especially important for distinguishing some types of Seyfert galaxies and quasars. Again, angle matters. Dust is not just decoration. It changes what the universe allows us to see. Blazars are a special orientation, but with jets rather than only dust as the main feature. If the jet points close to us, its boosted emission can dominate over many other components. The accretion disk may be hidden not by dust but by brightness from the jet. The host galaxy may be hard to see because the active nucleus overwhelms it. The emission lines may appear weak because the jet's continuum light dilutes them. The object becomes a beam first and a galaxy second, at least from our instrument's point of view. This can make blazars both easier and hard to study. They are easier to detect across great distances because the jet is bright and boosted. They're easier to monitor because they vary. They're powerful sources of gamma rays, making them important for high-energy astronomy. But they're harder to interpret because the jet can hide other parts of the system. Measuring the host galaxy, the accretion disk, or the line-emitting gas may require careful observation and modelling. The very feature that makes a blazar spectacular also makes it a little rude, scientifically speaking, because it talks over everyone else in the room. Quasars, when not dominated by a jet aimed at us, may allow a clearer view of the accretion disk and broad emission lines. Those lines can help estimate the mass of the central black hole and the rate at which it is accreting. The luminous disk can reveal how matter is falling inward. The surrounding gas can show chemical enrichment in the host galaxy. Quasars are therefore powerful tools for studying black hole growth and early cosmic history. Blazars are also tools for those questions, but they add jet physics, relativistic beaming, and high-energy emission to the mix. It is tempting to make a tidy ladder. Active galaxy at the bottom, quasar in the middle, blazar at the top, as if one simply becomes the next. But that is not quite right. The relationship is more like a family tree mixed with a set of viewing angles. All blazars are active galactic nuclei. Many blazars can be considered jet-dominated quasars or related to quasars, depending on their spectral properties. Not all quasars are blazars, not all active galaxies are quasars, not all active galaxies have strong jets. Some active galaxies are modest compared with quasars. Some jetted active galaxies are radio galaxies because we see them from the side. The labels are nested in some ways and angled in others. A simple version might go like this. An active galactic nucleus is the feeding black hole system at the centre of a galaxy. A quasar is a very luminous active galactic nucleus, often so bright that it outshines its host galaxy. A blazar is a jetted active galactic nucleus seen almost directly down the jet, so relativistic beaming makes it look especially bright and variable. That is not every nuance, but it is enough to keep the draw from becoming tangled. The historical names make the situation seem more complicated than the physics itself. Quasar came from how the objects looked when first discovered, like quasi-stellar radio sources. BL-lac objects were named after one object that was originally catalogued like a variable star. Seyfert galaxies were named after astronomer Carl Seyfert, who studied galaxies with bright nuclei and unusual emission lines. Radio galaxies were named because they were bright in radio wavelengths. These names reflect the order in which humans notice things, not a perfect map of nature. Astronomy carries its history and its vocabulary. Sometimes the names are charming, sometimes they're confusing, often they are both. What helps is to focus on the central engine. Is there a supermassive black hole feeding? If yes, we are in active galaxy territory. How luminous is it? If it is extremely luminous, we may call it a quasar. Are there jets? If yes, it may be radio loud or jet-dominated. Is one jet aimed close to us? Then we're likely dealing with a blazar. Are the emission lines strong or weak? That may help distinguish a flat-spectrum radio quasar from a BL-lac object. Is the view blocked by dust? That may change the apparent type. Step by step, the labels begin to behave. There is also a physical reason the viewing angle produces such dramatic differences. In ordinary life, changing your angle changes what you see, but it does not usually multiply brightness by enormous factors. Looking at a lamp from the front instead of the side may make it brighter, but not cosmically brighter. In a blazar, the jet is moving at nearly the speed of light. Relativistic beaming concentrates radiation along the direction of motion. The approaching jet is brightened. The receding jet is dimmed. The observed timescales are compressed. The spectrum can shift. So orientation is not a small detail. It is a major physical effect. This is why blazars are so variable compared with many other active galaxies. The boosted jet emission lets us see rapid changes from compact regions. A disturbance in the jet can produce a flare that looks dramatic from Earth. The same disturbance viewed from the side might appear weaker, slower, or be hidden among other emission. The object has not necessarily changed its behaviour. The observer has changed the way that behaviour is projected. Blazars are extreme partly because they are extreme engines, and partly because they are extreme alignments. The relationship between blazars and quasars can be especially confusing because some blazars are flat-spectrum radio quasars. That name contains both ideas. It means the object is a quasar-like active nucleus with strong radio emission, and a jet close to our line of sight. The flat-spectrum part refers to how its radio brightness changes with frequency, which is connected to compact jet emission. These objects often have strong broad emission lines, so they look quasar-like in their spectra, while also behaving like blazars because the jet is aimed toward us. A BL-lac object, by contrast, may have a spectrum so dominated by jet light that emission lines are weak or absent. So blazar is more about orientation and jet dominance, while quasar is more about luminous active nucleus behaviour. The two ideas can overlap. A flat-spectrum radio quasar is both quasar-like and blazar-like. A BL-lac object is a blazar but may not show the strong emission lines we associate with classical quasars. This is why the sentence, "a blazar is a kind of quasar," can be useful in a broad introduction, but a little too simple if we want to be careful. Better to say a blazar is a jet-dominated active galactic nucleus seen nearly along the jet, and many blazars are part of the quasar family or closely related to it. The host galaxy also plays a role in how these objects are understood. Many powerful radio-loud active galaxies and blazars are hosted by massive elliptical galaxies, while Seyfert galaxies are often found in spiral galaxies. This is not an absolute rule for every case, but it reflects patterns in how different active nuclei appear in the local universe. The galaxy's mass, merger history, gas supply, and central black hole all influence the kind of activity we see. A quasar in the early universe may be a growing black hole in a young massive galaxy. A nearby Seyfert may be a lower power active nucleus in a galaxy where the host is clearly visible. A blazar may hide much of its host behind a boosted jet. There is no shame in the categories being messy. They are human attempts to describe a continuous range of cosmic behaviour. Nature does not always place clean borders where our vocabulary wants them. Some objects sit near boundaries, some change state, some have weak jets, strong disks, unusual spectra, or rare alignments. Classification helps us think, but it should not become a cage. A blazar, quasar, and active galaxy are not separate boxes sealed from one another. They're connected views of supermassive black holes feeding inside galaxies. That connected view is the main thing to carry forward. A blazar is not an entirely separate monster from a quasar. A quasar is not separate from the larger idea of an active galaxy. They're all part of the story of matter falling towards supermassive black holes, releasing energy and sometimes launching jets. The differences come from power, environment, dust, jet strength, and viewing angle. A quiet galaxy has a sleeping or weakly fed central black hole. An active galaxy has a feeding one. A quasar has a very luminous active nucleus. A blazar has a relativistic jet aimed almost at us, making it bright, variable, and rich in high-energy radiation. Once this naming puzzle settles, the blazar becomes easier to recognize for what it is. It is not just a bright quasar with a fancy nickname. It is a special view into a jetted black hole system. It shows us the beam almost head-on. It lets us study relativistic physics, particle acceleration, magnetic fields, and high-energy radiation with unusual clarity. It also reminds us that the universe is full of objects whose appearance depends on our line of sight. Sometimes what we call a thing is partly what it is, and partly where we happen to be standing. By the time we look straight into the idea of a blazar, most of the pieces are already on the table. There is a distant galaxy, full of stars, gas, dust, and history. There is a supermassive black hole at its centre, not wandering through space like a monster in search of dinner, but sitting in the dense middle of its galaxy, shaping the region around it through gravity. There is a hot accretion disk, where matter spirals inward, rubs against itself, heats up, and releases energy before some of it crosses the event horizon. There are magnetic fields, stretched and twisted by rotation, helping to organize some of that energy into narrow jets. And there is our angle, the quiet little fact that one of those jets is pointed almost directly toward us, turning an active galaxy into one of the brightest beacons we can observe across the universe. That is what makes the beam so important. Without the beam, the object might still be a powerful active galaxy. It might still have a feeding black hole, a bright disk, and huge jets extending into space. But from Earth, it would not appear the same. The jet would not be aimed toward our telescopes. Its light would not be boosted in our direction in the same extreme way. Its flickering might not look so sharp. Its gamma rays might not stand out so strongly. The blazar is not only a thing, it is a thing plus a direction. It is a cosmic engine seen almost head-on. This is one of the great lessons blazars give us. The universe is not only built from objects, it is also built from relationships between objects and observers. That does not mean the universe depends on us in any special way. The blazar would still exist if no one on Earth noticed it. The jet would still race outward. The particles would still spiral through magnetic fields. The photons would still leave the source and cross space. But what we call it, what we measure, and how dramatic it appears are all shaped by where we happen to be. The same galaxy seen from another angle might be catalogued differently. From here, because the beam is nearly aimed at us, it becomes a blazar. Looking into that beam is not like seeing a close-up picture of the black hole. It is more indirect and in some ways more interesting. We do not receive a neat photograph of the central engine with labels attached, though that would be convenient. We receive light spread across the spectrum, changing over time, carrying signs of speed, magnetic fields, particle energies, and distance. Radio waves tell us about electrons spiraling through magnetic fields and about larger jet structures. Visible light and infrared show changing emission from the jet, and sometimes clues from the host galaxy or surrounding dust. X-rays and gamma rays show the highest energy processes, where particles have been pushed to extraordinary speeds. The beam is not a simple flashlight. It is a full report written in radiation, and the report has travelled for a very long time. Some blazars are relatively closer in cosmic terms, though still far beyond any ordinary human scale. Others are so distant that their light has crossed most of the age of the universe to reach us. When we detect one of those distant sources, we are not seeing the galaxy as it is right now in its own local present. We are seeing it as it was when the light began travelling. The farther away it is, the further back we look. Space becomes a kind of time machine, not because we can step into the past, but because light needs time to move. That means a blazar can be both a current observation and an ancient event. A telescope may record a flare tonight. Astronomers may plot the brightness on a graph and send out an alert. From our point of view, the blazar has brightened now. But the event that produced that light happened long ago, perhaps before humans existed, before mammals looked much like they do today, or even when the universe itself was only a fraction of its current age. The light arrives in our present, but it was launched from a different cosmic era. Astronomy often asks us to hold those two truths at once, and somehow both are correct. This is why the title idea of looking back across time is not just a nice phrase. It is exactly what deep astronomy does. Every star you see at night is seen as it was when its light left it. For nearby stars, that delay may be a few years, decades, or centuries. For distant galaxies, it can be millions or billions of years. For the farthest blazars, it can be light from a universe still young, still building many of its large structures, still feeding black holes that had somehow grown very massive very quickly. A blazar beam can therefore carry information from a stage of cosmic history we cannot visit directly. The beam also gives us a way to study physics under conditions that are impossible to create on Earth. Our laboratories can accelerate particles, generate magnetic fields, and measure radiation with extraordinary precision, but they cannot reproduce the full environment around a feeding supermassive black hole. We cannot build a black hole billions of times the mass of the Sun, wrap it in a hot accretion disk, thread it with huge magnetic fields, and launch a jet across intergalactic space, which is probably just as well. Instead, nature has built those laboratories for us. Blazars are among the clearest examples because their jets point nearly our way and make the extreme processes easier to detect. When we study the beam, we learn about particle acceleration. The jet must energize particles to speeds close to that of light. Electrons spiral in magnetic fields and emit synchrotron radiation. Photons gain energy by scattering from fast electrons. In some models, protons and other heavier particles may also be accelerated, possibly connecting blazars to high-energy cosmic rays and neutrinos. All of this is hidden inside what may look like a point of light. The point is small only because the source is distant. The physics inside it is enormous. The beam also teaches us about magnetic fields. Magnetic fields near black holes are not decorative background details. They can help launch jets, shape them, guide particles, and store energy that may later be released in flares. When astronomers measure polarization from blazars, they're gathering clues about how those magnetic fields are arranged. A change in polarization during an outburst may suggest that the field has become more ordered, less ordered, twisted, or disturbed by a shock. The light is not just bright or dim, it has structure. Even the orientation of the light carries a memory of the invisible fields that helped create it. Variability gives us another kind of information. A blazar's brightness can change quickly, and those changes act like a ruler for the emitting region. If the light rises in a short time, the region producing it must be compact enough for the change to happen coherently. This can reveal small zones inside a jet that is otherwise enormous. A flare may come from a shock moving through plasma, a burst of magnetic reconnection, a turbulent region, or a fresh injection of energetic particles from the central engine. Whatever the cause, the flicker tells us that the beam is not a smooth, unchanging stream. It has weather inside it, if we can borrow the word carefully. Not clouds and rain, of course, but patterns, disturbances, and moving fronts of energy. Relativistic motion shapes the whole view. Because the jet is moving close to the speed of light and almost toward us, its emission is boosted. The observed brightness is enhanced. Timescales are compressed. The source can appear more extreme than it would from another angle. This is not a trick in the sense of being false. It is a real physical effect of motion and light. The universe is showing us what happens when speed, direction, and radiation combine under Einstein's rules. A blazar is therefore one of the best reminders that relativity is not only something written in equations, it is active in the sky. At the same time, cosmic expansion changes the light during its long journey. Wavelengths stretch. High-energy photons can interact with background light. The signal may be dimmed, reddened, or partly absorbed depending on what it crosses. So the beam does not only tell us about its source, it tells us about the space between the source and Earth. A distant blazar is like a bright lamp shining through a vast room filled with faint traces of cosmic history. By studying what arrives and what is missing, astronomers can learn about the background light produced by generations of stars and galaxies. The beam becomes both message and measuring tool. There is something deeply practical about this despite the scale. Astronomers do not simply say, "That is bright," and move on, though one could hardly blame them for pausing there. They measure the spectrum, they record the timing, they compare wavelengths, they check polarization, they identify redshift, they model the jet, they look for connections with neutrinos or cosmic rays. They ask whether the light came from close to the black hole or farther down the jet. They ask whether the flare was caused by electrons alone, or whether heavier particles were involved. Each question narrows the picture a little more. This is how a blazar becomes understandable, not all at once. Not in one dramatic revelation. It becomes understandable through many small acts of measurement, repeated patiently across years. A radio telescope observes the core. A gamma-ray telescope records a flare. An optical observatory tracks brightness changes night after night. An X-ray satellite measures the high-energy slope. A spectrum reveals distance. A polarization measurement hints at magnetic order. None of these alone is the whole story. Together they turn the beam into a physical object with structure, history, and behavior. And still, even after all the measurements, the simple image remains powerful. Somewhere in a distant galaxy, matter is falling toward a supermassive black hole. Some of it heats and shines, some crosses the horizon and is lost to the outside universe. Some energy is redirected outward through magnetic fields and rotation, becoming a jet. That jet travels through the galaxy and beyond, carrying particles and radiation at nearly light speed. One side of the jet points nearly toward Earth. Its light is boosted along our line of sight. After travelling for millions or billions of years, that light reaches our instruments. We call the object a blazar. The word itself may feel sharp and modern, but the object is ancient in every meaningful way. The light is old. The black hole may have grown across enormous spans of cosmic history. The galaxy may have formed through mergers and gas flows long before the sun was born. The processes inside the jet rely on physical laws that have been operating since the early universe. A blazar is not a new thing because we named it recently. It is a very old phenomenon that we have only recently learned to recognize. There is also no need to imagine the blazar as a danger. These beams are powerful, but the blazars we study are extremely far away. By the time their radiation reaches us, it is a signal for instruments, not a force that disturbs ordinary life. The atmosphere protects Earth from many forms of high-energy radiation, and space telescopes detect what cannot reach the ground. The beam may have begun near one of the most violent environments in the universe, but here it arrives as data, as a tiny count in a detector, as a point on a graph, as a clue. That transformation from violence to information is one of astronomy's quiet comforts. It also changes the way black holes feel in the imagination. They're often described only as endings, places where matter disappears and light cannot return. That is true at the event horizon, but it is incomplete as a picture of real black hole systems. Around feeding black holes, the universe can become brilliantly active. Disks glow, jets launch, galaxies are affected, particles accelerate, radiation escapes. A black hole can be dark in itself and still be connected to some of the brightest structures we can see. In a blazar, that contrast is at its strongest. Darkness at the centre, brightness in the beam. So what is a blazar really? It is a galaxy with an active centre, powered by a feeding supermassive black hole. It is a relativistic jet aimed almost directly toward Earth. It is a source of radiation from radio waves to gamma rays. It is a rapidly variable object whose flickering tells us about compact regions moving at enormous speeds. It is a probe of magnetic fields, particle acceleration, black hole growth, and the light between galaxies. It is a cosmic lighthouse, yes, but not one built for us. It is a beam we happen to stand within. That happenstance is worth appreciating. Our planet is small, our solar system is ordinary in many ways. The Milky Way is one galaxy among many. And yet, from this small place, we can detect beams from galaxies across the universe and use them to learn how black holes grow, how jets form, and what the young cosmos was like. There is no need to make Earth central for this to feel remarkable. In fact, it feels more remarkable because Earth is not central. We are not the focus of the blazar. We are simply awake enough, briefly enough, to notice the light passing through our part of space. Perhaps that is the quiet lesson at the end of this journey. A blazar is not only an answer to an astronomy question, it is a reminder that the universe often looks simple until we learn how to ask better questions. A point of light becomes a galaxy becomes an active nucleus becomes a feeding black hole becomes an accretion disk, a magnetic field, a jet, a spectrum, a light curve, a time capsule, and a clue to the early universe. The deeper we look, the less empty the darkness becomes. If you are still listening now, wherever you are, take a moment to picture that beam crossing space. Not rushing for your benefit, not hurrying toward a conclusion, just travelling because light travels. It leaves a distant jet, crosses the spaces between galaxies, passes through the long history of the universe, enters the neighbourhood of the Milky Way, moves through the solar system, reaches Earth, and is caught by an instrument built by minds that evolved under one small star. The journey is enormous, the arrival is quiet, and somehow from that quiet arrival we learn. So the next time you hear the word blazar, it may no longer sound like just a strange astronomical label. It may carry the image of a restless galaxy, a hidden black hole, a jet pointed nearly toward us, and a beam that has crossed time to reach our telescopes. It may remind you that the brightest things in the universe can begin near the darkest ones, and that even a faint point in the sky can contain a story far larger than it first appears. And now, as our thoughts drift back from those distant jets to the room around us, the universe has not become smaller, but maybe it has become a little more familiar. The Blazar remains out there far beyond reach, still changing, still shining, still sending light across space. Here, in this quieter place, we can let the idea settle without needing to chase every photon. We have followed the beam as far as we can for tonight, from the black hole's surroundings to the edge of cosmic time, and back again to this moment where the science can soften, the questions can rest, and the dark above us can feel less empty than before. If this journey helped you unwind, if it gave your mind something calm and vast to wander through, I would be ever so grateful if you liked the video, subscribed, or shared this sleepy corner of science with someone who might enjoy drifting through the universe at a gentle pace. And wherever you are listening from, whether the sky outside is full of stars or hidden behind city lights, remember that somewhere far beyond what our eyes can see, beams from distant galaxies are still crossing the universe, carrying old light through deep time. Sleep well, fellow traveller, and may your own little corner of the cosmos feel quiet, steady, and wonderfully safe tonight.